This is StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And today, we're featuring one of our one-on-one conversations, this time with Professor of Theoretical Physics, Kip Thorne. Kip Thorne, welcome to StarTalk.
A pleasure to be with you, Neil.
Oh my gosh, we are coming from your home office. My first exposure to you was you were one of the three authors of this book called Gravitation. This book is a graduate level treatise on basically Einstein's general theory of relativity. It was brilliantly conceived because I don't know if you can notice on camera, there are tabs are different colors, it's white and black. They represent two different paths through the book. One is sort of the elementary path and one the more advanced path, except it all looked advanced to me at the time. So whose idea was this to come up with this book?
Coming up with the book, I think it was sort of grew out of discussions that Charlie Misner, John Wheeler, my PhD advisor, and I had a few years after I got my PhD.
Those are the three co-authors there.
Those are the three co-authors. Mm-hmm. And so it sort of grew organically in the...
That's the best kind of projects to have.
1960s and early 1970s.
On here is Charlie Misner, who's was at the University of Maryland.
Yes.
And so my copy of this, I had you sign it. And then I spent a year teaching at the University of Maryland. So I quickly went over to his office and had him sign it. But before then, I started out in graduate school at the University of Texas, where John Archibald Wheeler they stole him from Princeton, I think, is what that. And so I had all three of them sign it. In fact, John Wheeler's course that he taught in general relativity is where I met my wife.
Wow.
Yeah, she has a PhD in mathematical physics. So we met in relativity class. And John Wheeler used to give out a penny if you caught an error that he committed on the front board. So I have one of his pennies. It was a typo or something, or the written version of a typo. But so anyhow, it's just a delight to meet again with you. And what prompted this was our, you have a lot of accolades, of course. More importantly than that, you were science advisor on the film Interstellar.
Well, I was more than science advisor.
Yes, you were. You were executive producer.
I was more than executive producer. It grew out of a treatment that Linda Opes, an ex-girlfriend of mine.
Oh,
and
Linda Opes, a big producer of sci-fi films.
Yeah, she a big producer of films of a wide variety. But Linda and I dated in 1979-80, and it was some years later after Carl Sagan, who set us up on a blind date, by the way. That's how we met.
Okay.
Some years later, Linda called me up and said, "Would you like to brainstorm with me for a movie?"
Wow.
And we did, and that's how Interstellar was born.
So was that at the time?
It really was the creation of the Nolan brothers, because they took what we had given them, which was basically a structure and a venue for the movie, The Warped Side of the Universe. And they ran with it and changed our story almost completely and made it into a great film.
It's at the time, I mean, you're a professor at Caltech, the Richard Feynman professor at Caltech, now emeritus. Caltech is a pretty high-level place. How was it viewed for you to say, guys, hold on, I'm going to make a movie now? How does that received by your colleagues?
I think they were all enthusiastic.
Good.
Caltech is a different kind of a place than some other more stuffy university.
Okay. I never hung out much at Caltech, so I couldn't judge the mood or the tone.
Yeah, no, look, we're on the edge of Hollywood. The Hollywood folks come over and, Big Bang Theory was based on Caltech.
Right, they didn't call it Caltech. What did they call it?
They did call it Caltech in the first few episodes.
Okay.
And then they stopped using the Caltech name because the shirts, that's Hollywood speak for the attorneys. The shirts got scared that they might do something on a screen that the Caltech shirts wouldn't like, and the Caltech shirts might sue. Okay. So they stopped using Caltech name.
And in the film, which I adored, what was it called? Real Genius?
Yeah.
Real Genius. They were at Pacific Tech. All right. That was where all the smart kids were. So, of course, Pasadena is in, I can't say foothills of Hollywood, but you have a proximal awareness of this huge industry, and you know that science fiction matters as a genre.
Well, and some of us love it.
And so Interstellar, I think it introduced many people to authentic gravitational physics for the very first time.
Well, Interstellar was unlike almost any other film. I think there were precursors in 2001 and in Contact.
Yeah, Carl Sagan's Contact.
Carl Sagan's Contact. And the point is that science, lots of science was baked into that film from the very beginning because of the way it was born and because of the close collaboration I had with the Nolan brothers, built in right from the very beginning. And baked in, and a science in which the guideline that we worked from is that nothing in the movie would violate well-established physical laws, and all the wild things would at least spring from science in some manner.
As any good science fiction story should be. But there's not enough.
Well, there's nothing wrong with fantasy films, the Harry Potter style, for example. It's just a different genre.
By the way, that film, you must have known. You said, okay, we're going to have to help people out. Give a guy a break, okay? They're trying to see the movie. They're trying to follow what's going on. What the hell's happening? Why did the guy get old? Why is he younger than his mother? What's going on? And you upped and said, let's help a person out.
Yeah, well, I would put it a little differently. Okay. I saw it as a superb opportunity to use this film as a motivator to get people interested or intrigued in science. And then there would be a bridge to science through this book.
So The Science of Interstellar, New York Times bestseller, Kip Thorne, with a foreword written by, of course, Christopher Nolan. And it says, spoiler alert, this book explains the fantastic climax and ending of Interstellar.
And so let me tell you how this issue came about. Chris said to me early on, I would like to make a film where the ending is as mysterious as the ending of 2001, A Space Odyssey.
That's a high bar.
That's a high bar, but he greatly admires Stanley Kubrick and that film. And so somewhat later on, as we were talking about the ending, and we had lots of conversations about the ending, he said, well, you can explain the ending in this book.
So he volunteered you to write the book.
Well, no, I was already planning to write the book, but he identified that as the place where the ending will get explained. He was not going to explain the ending. He would leave it mysterious.
Not in his film. He was pulling a Kubrick on us.
That's right.
In fact, we interviewed Christopher Nolan. If you're an archive diver, we've got a whole episode with Christopher Nolan, even before Interstellar was produced. And as we know, so many of his movies, he plays with time in some kind of interesting way. If I remember correctly, he talks about how influential 2001 A Space Odyssey was to him back in 1968. That would have been.
Yes.
So let me ask you just a couple of things about the storyline. And I have an issue with it, if I may. But I don't know if I ever went public on this, but I figure I'm in front of the man himself. So I guess my issue, we're looking for a planet. Again, this is in the themes of the movie. We're looking for a planet like Earth, similar enough to Earth that we can send people there to continue our civilization and our species. Is that a fair characterization of a plot line, of the plot line? Okay. And it turns out there's like a wormhole that can make that happen a little faster, because otherwise you don't live long enough to travel the distances with the rockets available to hit those destinations. Okay. I'm just thinking, this blight on the crops that was starving everyone on Earth, requiring that we jump ship, it seems to me that whatever effort it takes to find another Earth, travel through a wormhole, terraform it, ship 1 billion people there, whatever that effort is, seems to me to be a bigger effort than just telling the biologist, come up with a serum that could fix the crops. Even today, we have full knowledge of crop genomes. Isn't that cheaper, easier, faster than wormholing your way off this planet?
So you think that all problems can be solved by humans with human technology. Let me describe, this characterizes how this movie was done. So when Jonah Nolan, Chris's brother, who came up with the idea that he wanted a blight or something like that. And so we said, okay, we will bring together the best biologists we can, who are experts on these kinds of things, put together, mostly Caltech biologists, and we had a dinner. So we had a conversation that lasted about three or 4 hours at the Caltech Faculty Club, the Athenaeum, about what would be the best backstory here. There are two types of blights. There are generalized blights that attack lots of crops. And there
lots of different species of crops.
Lots of different species of crops. They are generally fairly benign blights. And then there are blights that are very specific to a particular crop, and they can be very lethal blights. May totally wipe out that species on Earth even. But basically for Earth and life on Earth to survive, you better not have a vicious generalized blight. But according to the biologists that I discussed this with, they didn't know of anything that would prevent the development of a very vicious generalized blight. So that's what occurs in this movie. And it's something that biologists have never seen, but they cannot rule it out.
Okay, so let me repeat what I think you said. They have vicious, lethal blights that attack a species, less lethal generalized blights that cross species boundaries, and they can't rule out a lethal blight that would cross species.
That's right. This film is full of backstories because of the way we did it. As I say again, it's unlike almost any other film, in that these issues were vetted by the world's best experts in the process of the writing of the screenplay.
Okay. When they're on the black hole planet, and then they see this wave coming. Okay,
it's Miller's planet.
Miller's planet,
that's the water planet.
The planet orbiting Gargantua.
Mm-hmm.
Gargantua,
yeah.
Okay. The strength of tidal forces are highly sensitive to the distance you are to that which is causing the tides. Highly sensitive, okay? But every illustration I've drawn or taught about tides, they're not so peaky. They're much broader in their representation on a planet. And so there they are, wading in water, but then they see this single wave come. And if it is a single wave, as we've seen with tsunamis, it actually takes water away from what's ahead of it. Because it can't just be water out of nowhere. It's drawing water from its vicinity. So my two issues was, if it's tidal, would it be that peaky? And if it's any kind of wave, how could it still leave the water laying around its vicinity and then just be that big as it came by?
So there is a type of wave called a solitary wave. This particular kind of wave was discovered in the 1700s by a physicist in England who saw a boat that was being pulled by horses, and it was just starting up, and it created this wave that traveled down a canal, and it was peaked like the wave in Interstellar, though the wave in Interstellar, I have to admit, it was exaggerated.
I don't mind exaggeration.
There was some exaggeration in the peak, but it traveled down the channel. It never broke. Most waves in the ocean, they break.
Okay, just so we can get the picture, because we're talking about centuries ago. When you say a channel, that would be a channel or a canal.
A canal.
And then there's a towpath on the side.
And
then people, and more likely beasts of burden, would drag things through the canal. Because canals themselves don't typically have currents.
Drag a barge down the canal.
A barge, exactly.
Yep. And so this barge was dragged down the canal, and it was just starting up, and it created this wave.
On the startup.
And it just headed out and just took off and went down the channel. And this guy got on his horse, and he went down the channel for, I don't know, a mile or two without changing its shape, without
breaking.
And so the theory of these waves is that there are two different effects that cause a wave to steepen or disperse, and the two can balance each other out in a stable sort of a way.
And give it longer life.
And give it a long life. And so aside from the issue of friction, if there were no friction, it would just live forever and
Sure.
keep propagating in a very stable way. There's a mathematics behind it, something called the Korteweg-de Vries equation. But anyway, these waves then...
So that equation, I presume, has both kinds of waves in equilibrium somehow represented
the two
as a
effects,
static wave.
the dispersion and the steepening. The steepening is due to nonlinearities. The dispersion is due to the fact that the higher parts of the water travel faster than the lower parts of the water.
I didn't know that.
If you're at the ocean, you see a little tiny wave, it travels quite slowly. You see a big wave, it travels quite fast.
And that's why the crest of the wave will actually break before the rest of the wave gets there.
That's right.
Is that part of the reason?
That's right. Unless that's being balanced out. The two effects balance each other and to produce this very stable solitary wave. And so in the movie, for this stable solitary wave, the height of the wave is, and I've forgotten the number, but it's something like 6 times higher than the depth of the water.
Got it.
So there's a problem now in the movie because they're walking around in shallow water and this wave is high. And so it's got to be deep water.
Okay.
But they're on an island. This is the backstory. Again, there's always a backstory.
So they're on a subterranean, a subsurface island.
Yeah. And this wave diffracts around the island. They hardly notice the island at all. So again, it's all explainable, except there is a bit of exaggeration.
And we'll give you that. We'll give you that. It's a movie and it's Hollywood.
Yeah.
But what you're saying is this wave might have been caused by some effect other than the tidal forces of the black hole.
Yeah. Well, this wave is caused, in fact, by the fact that this time is much slowed on this on this planet. So the planet has been put into the orbit around Gargantua not that long ago, as seen on the planet, though it's a long, long time ago, as seen from far away. And it's like Mercury, like the moon keeps one face toward Earth, or Mercury keeps one face toward the sun due to tidal effects. This planet is distorted by tidal effects, and it's swinging back and forth. It has not yet settled down to one face toward the planet, and that swinging back and forth is generating this wave.
We took our show to Oxford recently, and I interviewed at Oxford, I think it was a postdoc, and his name is Andrew Mummery, postdoc, and he showed us a recent paper he published. I don't know if you've seen it recently, like within the past 18 months. And he's a theoretical physicist. And he alerted me to something I'd never knew. I love the field, but it's not my active professional field, that in the vicinity of a black hole, there is an innermost orbit, because of course you can orbit any source of gravity, even if it's a black hole. But for black holes in particular, there's an orbit within which the orbit is no longer stable and it will spiral into the black hole itself. And according to his calculation, to get the time dilation necessary in the scene with the black hole planet, which was huge. Remember, they were on the planet for like 15 minutes or whatever. How long?
Well, 1 hour on the planet is 7 years up at high altitude.
7 years up in their spaceship, okay? And the guy who they left there, he's like gray and unshaven and everything. And we're like, oh my gosh, there's some serious Einsteinian physics going on here. His calculation showed that for that difference, for that extreme difference in time dilation, requires that planet orbit so close to the black hole that would be on an unstable zone. And so I just thought I'd tell you that.
My calculation says otherwise. If you want to derive the formula, that's a lot of work. So let me tell you the story behind this.
So everything's got a story. Okay.
So Christopher Nolan says to me one day, he says, I want Cooper, the hero in this movie, to go down onto this planet.
Cooper, played by Matthew McConaughey.
Yeah, that's right. Professor Brand's daughter is played by Jessica Chastain. Christopher Nolan says to me, he says, I want in this movie that 1 hour on Miller's planet is 7 years up at very high orbit or back on Earth. And I said to him, that's impossible because the planet will fall into the black hole. He said, go do a real calculation. I've already learned that your off-the-cuff reactions can be wrong. And I should not trust you unless you do a real calculation.
There's a good Hollywood producer. Go back and give me the answer I'm looking for.
Well, and so I went back home and I did a real calculation and I was amazed. The last stable circular orbit, which is what we're talking about, if the black planet spins fast enough, the last circular stable orbit can have as high a redshift, as high a time difference as you might wish. But that requires
the dilation.
It requires that this black hole spin extremely close to the maximum possible spin. And so in the book, I give the formula for what is the spin of the black hole that is required to produce a given amount of slowing of time.
I did not know that.
And so it's an approximate formula, but it's a formula that can be derived, though it takes a fair bit of algebra.
Okay, so the one would just learn about would probably be the lowest stable orbit around a non-rotating black hole.
That's right,
and that's a clean.
That's a clean problem, and that's what I was thinking when Chris said I want this. And I knew that if I made the black hole spin, that it would get closer, but I couldn't imagine that nature would provide it for a black hole that spins fast enough that they could provide this much of a slowing of time. But it does. It does. At least. Unless I made a mathematical error.
It's not just an analytic solution.
Well, it is an analytic solution.
But it's very complicated.
But it's very complicated. Yeah.
Okay.
Well, it's a power series solution.
In the end, I think our hero character is inside the black hole. We come to understand this. And he has access to a timeline that wouldn't otherwise be available to him. And he sees his daughter's bookshelf.
Well, he's no longer inside the black hole.
Where is he when he's doing this?
So this is the key thing that's not explicit, that you only understand if you read my book. When he gets inside the black hole, he is scooped up by a spacecraft that was built by this advanced civilization that provided the wormhole to him and to humanity. And it's called the Tesseract. And Tesseract is a four-dimensional cube. 4 spatial dimensions.
And that's why in there you saw, I guess, the past and future all kind of simultaneously.
All related to
it felt very higher dimensional.
Yeah, so that's right. So
he succeeded there.
This Tesseract, so let me back up. I'll tell you a story. So early on when we were working on the film, Christopher Nolan said to me he wanted to take his hero back to Earth, Cooper back to Earth, by a different route than the wormhole, 10 billion light years away from the Earth. How's he going to do it if it doesn't go through a wormhole? He said, well, I want to take him back faster than the speed of light. And of course, I say to Chris, you can't do that. It violates the laws of physics. We discussed this for a week, and then he threw in the towel. He said, okay, I believe you. And so what do we do? And so I said, well, you put him, he goes inside the black hole. He gets deposited on the 3-dimensional surface of a 4-dimensional sphere, and this 4-dimensional sphere is a spacecraft that can go into the bulk, into the higher dimension. And it goes out of the black hole, not through the horizon. It can't do that. It goes up
through the 4th dimension.
Up through the 4th space dimension, or what's called the 5th dimension in the movie.
Sure.
This time is the 4th dimension, and goes back to Earth. And the distance back to the Earth is less than the distance between the Earth and the sun. Even though it's 10 billion light years inside of our universe, up in the bulk, it's a very short distance. And so he can get back very quickly.
This is the higher dimensional space-time in which we are now having this.
So he gets back very quickly, riding on the surface of this 4-dimensional sphere. He said, I like it all entirely, except I'm going to use a 4-dimensional cube instead of a 4-dimensional sphere. That's a tesseract.
Yes.
And so that's what happens. And when you see Cooper out there sort of flailing around, beginning of the Tesseract scene, he's being carried by the Tesseract back to Earth, but you don't know that's what's happening until you read my book. So anyway, he's carried back to Earth, and then everything is happening when the Tesseract is docked in the higher dimension.
Giving access to his life in that past time.
That's right. So it's docked in his home in his daughter's bedroom.
Okay, so now he's pushing books off the shelves that land on the floor, and through some clever cryptographic judgment, he's spelling out words with the first letter of the title of each book. Okay, here's my issue. I had no problems with Tesseract, black hole, fourth dimension, 5 dimensions. How does he know the title of each book from the other side of the book?
So I don't remember that's how he's actually.
He's pushing books out.
No, I know he's pushing. He's pushing
books out from this side.
Yeah.
And all he sees is the other side of the library shelves.
I guess I had forgotten that he was spelling things out.
What's this I hear that you can use a wormhole to travel backwards in time? Does the math check out? Does the Einsteinian physics check out? And does that mean I will just show up a younger version of myself and shake my own hand? Is that what you mean by that? Or do I no longer exist in the time that I left for my younger version of myself to see that? And didn't Hawking put forth a time travel prevention conjecture or something? What's going on there?
So this is all an outgrowth of my phone conversation with Carl Sagan. He triggered me to start thinking about wormholes. And then having started to think about wormholes, it became pretty obvious to me rather quickly that if I give my wife, Carol Lee, one mouth of a wormhole, and she carries it at high speed in a rocket ship out into space and then back, and I keep the other mouth at home, and if she sees me age by 50 years back on Earth, well, she ages only 1 year going out and coming back. But if we look through the wormhole at each other, we see each other aging at the same rate. Just imagine we hold hands and we look at each other's wristwatches. It's ticking away at the same rate. So through the wormhole, we've aged at the same rate. We're the same age. Looking outside the wormhole.
Through a normal universe.
She's aged 1 year and I've aged 50 years. Something weird has happened. The wormhole has become a time machine. If I just go over and go into her wormhole mouth, and come out, I'll meet my younger self.
Okay, now Hawking said, no, we're not going to allow this. There's some conjecture yet to be discovered that'll tell you can't do that.
Well, so the story, we get there. You're going too fast.
I'm going too fast. Sorry.
So then I talked to friends at the University of Chicago. Physics, it's crucial to talk to friends. They tell you where you're all at. They tell you when you made a mistake. They straighten you out. And they pointed out to me that it might be that when the time machine is turned on, it'll self-destruct, basically, they said. And I said, I don't understand. They said, go do a calculation. So I went and did a calculation. And the issue is, and they had guessed, and basically, that's oversimplified, but Bob Garroch and Robert Wald at Chicago. Anyway, it turns out that at the moment that you can first time travel, the first thing that goes through, it can be vacuum fluctuations of light, say, that enter her mouth of the wormhole, come out of my mouth and go back and arrive back at her mouth at the very moment they started out. Now you have twice as much at the same place in space and time.
So this is a runaway.
So it's a runaway. And so you now have twice as much, and then it goes around again. Now you have 4 times as much, goes around again. So this runaway builds up.
Just like the feedback between a microphone and a speaker.
Precisely.
And it just runs away.
It just runs away. And it runs away. And this runaway shows up in the quantum mechanical calculation that I did.
You're bumming me out, dude.
Together with Sung-Won Kim, a Korean postdoc of mine. Anyway, we discovered this. Stephen, I think, and one of his, Stephen Hawking, and a student of his, I think, had more or less the same discovery at the same time. Except Stephen probably just did it all in his head, because that's the way Stephen is. Anyway, so then Stephen and I started corresponding about it by email and talking on the phone about it and so forth. It appeared to me, looking at the details of the calculation, that in fact the explosion, if I designed the time machine just right, the details of the explosion would not be strong enough to destroy the wormhole. And Stephen then showed me that I was wrong. And we argued back and forth for a while. And finally we came to agree that the explosion becomes strong enough that quantum gravity enters in and then holds the answer tightly in its grip. And so we won't know whether the time machine self-destructs until we understand the laws of quantum gravity.
So let me be fun and obscure here.
But then we come to the Hawking's cosmic censorship conjecture.
That's what it's called.
Yeah. The conjecture that, in fact, in the end, the laws of quantum gravity won't save the day. The wormhole will be destroyed, and any time machine that any advanced civilization makes will be destroyed when they try to turn it on by these vacuum fluctuations, and thereby, as Hawking says, keeping the universe safe for historians of all species.
It reminds me of the ultraviolet catastrophe, where you run the calculation, this is going to blow up. How does this even work?
Yeah.
And then out comes the discovery of the quantum, which saves the day, right? And this could be a calculation waiting for another branch of physics to open, or another progress in the known branches of physics to resolve.
The LIGO team has perfected a technique called quantum precision measurement, which is based on manipulating vacuum fluctuations in order to circumvent the uncertainty principle. And so this business of manipulating vacuum fluctuations is something we do in modern physics.
If memory serves, Carl Sagan came up to you and said, for contact, I want to go far distances quickly. How am I going to do it? Can you cook up a wormhole for me?
Carl phoned me, and he said that he'd already written the book, the novel. It was already in page proofs. And he said, I've got this novel, it's in page proof. The publisher's not going to be happy if I change it, but I really need some help, see what the truth is, and then we'll figure out how to deal with this. And he said that I have my heroine traveling through a black hole to get to the star Vega. And I said, you can't get through, get to the star Vega. So what you actually need is a wormhole. But there is an issue that wormholes implode. They collapse so quick that nothing can get through. So anyway, I figured out that if you had what I like to call exotic matter that repels gravitationally, and you put it inside the throat of a wormhole, that can hold the wormhole open.
It'll be like pushing it outward.
Yeah, that's right. It basically repels the walls of the wormhole to hold them open. And it turns out that will do it. But you have to have enough exotic matter to hold the wormhole open. And I deduced a formula for how much you had to have. And it basically says the following. You travel through the wormhole as close to the speed of light as you possibly can. Just very close to the speed of light. And you add up all the energy density all the way through the wormhole of stuff that's in the wormhole. The net has to be negative, and then you can hold the wormhole open. So it basically means you've got more negative energy than positive energy.
And we have nothing known as exotic matter.
Oh, yes, we do. I learned about this from Yakov Borisovich Zeldovich in Moscow. Zeldovich was one of the inventors of the Russian hydrogen bomb.
Okay.
And I learned this from him.
All right.
Okay. He was really brilliant. I learned about vacuum fluctuations and how important they can be and how powerful it can be if you can manipulate them. And so if you take a box and you remove everything that can possibly be removed from the box, you're left in the end with tiny fluctuations of everything that possibly could have been in the box. Electric fields, you have fluctuating electric fields, fluctuating magnetic fields, fluctuating protons, electrons, fluctuating deGrasse Tysons.
So this creates a form of pressure inside the box?
Well, so there's vanishing pressure and not vanishing energy due to renormalization. Now that's a nasty word in physics, but you can measure energy by whether it produces gravity or not. And although these fluctuations that are there, you can think of them as particles, say particles of light, flashing in and out of existence randomly.
So why isn't this not the virtual particles that people speak of?
So it's virtual particles.
It is that. Okay. We've spoken about those on our show before.
Okay. So you have virtual
with
particles.
Brian Greene, in fact.
So you have virtual particles in the vacuum.
Popping in and out of existence.
Popping in and you can't stop it. You can't prevent it. However, you can take fluctuations from one region and borrow them and put them in another adjacent region for a little while. Or if you put an electrically conducting sheet of superconducting metal here, then that will suppress the fluctuating electric fields parallel to the metal, because they would create an infinite current flowing in that metal. That would wipe out the electric field parallel to the metal. And so,
is that an element of the Casimir effect?
Yes, that's the Casimir effect.
It is, yeah, where you have two parallel plates evacuated between them.
That's right.
And there's a point where they actually feel a whole other force attracting them.
And so what that force really is in the region between them, the vacuum fluctuations are suppressed. And so you have negative energy in between. And that negative energy is sucking them together. And they can do work on you if you're holding on to these plates and they attract each other.
You have to put energy to resist it.
You put energy in as they go together. They do work on you. The electromagnetic field between two plates in the Casimir effect is exotic. Let me just say as a side remark, having learned a lot about vacuum fluctuations, we in LIGO, in our gravity wave project.
Oh, we get to that. I want to get to that.
But I'll just make the remark that the LIGO team has perfected a technique called quantum precision measurement, which is based on manipulating vacuum fluctuations in order to circumvent the uncertainty principle. And so this business of manipulating vacuum fluctuations is something we do in modern physics. And it is something then that you can imagine, you can ask, can a very advanced civilization manipulate vacuum fluctuations adequately in order to make enough exotic matter inside a wormhole to hold the wormhole open? And so I posed this as a question to my physicist colleagues, stimulated by Carl Sagan and him wanting to send his heroin through a black hole. I said, no, use a wormhole. And so we got to hold it open. Can an advanced civilization do this? Mm-hmm. And the answer is we still don't know. 40 years later now, we still don't know.
Right. Well, we're doing magic compared to what anyone thought was possible 50 years ago. Certainly at the dawn of quantum physics, we're on the centennial of the decade of quantum discovery back in the 1920s.
Right. Well, I was very close friends with Carl Sagan, and I've developed close friendship with Christopher Nolan. Chris has a very different background than me. He knows a lot of science, but he's learned it all by browsing the web. And he knows it well enough to ask me hard questions. So he has inspired me to ask questions that then I sort of translate to and give to a colleague. My role is to pass on interesting questions.
You're the conduit for this.
Conduit for interesting questions for my colleagues.
Dude, you can't leave well enough alone. Einstein says maybe there are gravitational waves emanating from major gravitational disturbances in the universe, and you got to go up and find them. But you're not the first to have attempted this, right? At the University of Maryland, there was Weber, I think. What's his first name?
Joe.
Joe Weber,
Joseph
of course,
Weber.
Who had a cylinder, if I remember correctly, where he was trying to measure whether if a gravitational wave washed over it, he could detect a distortion in the shape of the cylinder, I think was the goal.
Yeah, well, the gravitational wave would drive vibrations of the cylinder, end-to-end vibrations.
Okay.
And so he instrumented it to search for changes in the amplitude and phase of vibrations of the cylinder. The cylinder is at a finite temperature, so it's always vibrating a little bit because it's a finite temperature. And so he instrumented it with what's called piezoelectric transducers that he glued around the middle of the cylinder, that when they were squeezed, they would generate an electrical voltage that he could measure. And they're amazing things. piezoelectric transducers, just absolutely amazing. You squeeze them a tiny, tiny bit and you get a big voltage out. And I mean, Joe Weber was tremendously creative. He was,
I think he was working on that while I was at the University of Maryland. I was there in the 80s. I think he was still working on it.
Yeah, that's right. So he began working on it in the late 60s, early 70s, and announced that he was seeing possible evidence for gravitational waves. There was
a lot of skepticism at the time, if I remember.
Right. I'm sorry. He started working on it in the late 50s, early 60s, announced in 69 that he was seeing some possible evidence of gravitational waves. A number of other physicists around the world built similar detectors. And the bottom line in the end, after a period of shaking out, was that others were not seeing gravitational waves.
And that's the only way science works. One person's result is not a result until somebody else, a competitor, somebody else who uses different wall current, somebody from another country. You need multiple verifications.
But on the other hand, Weber, Joe, he started the field. He triggered this work. The approach that he invented for searching for gravitational waves was the dominant approach from then until the 2000s. And a number of other research groups built similar detectors and improved them better and better and better on that model. The model. So I mean, I have enormous respect for what he did.
Sure. Now you decided to, you and others decided to look differently for them.
Yeah. Well, so Rainer Weiss, Ray, his friends call him, at MIT, was the primary inventor of an alternative technique that was the technique that ultimately succeeded. He wrote a technical paper about the technique that identified all of the kinds of noise that you would have to deal with, and it explained how you might deal with them, and did analysis of how good this detector could be. It was a recipe for how to go forward. And he wrote this in 1972. And Ray, being Ray, didn't publish this because I think he figured you don't publish until you have built one and seen a gravitational wave. But however, Ray sent copies of this around to all his colleagues. And he put it into quarterly reports of the MIT laboratory in which he worked. And so it is probably the most influential non-published paper, certainly that I know of in physics. I mean, it was a tour de force, and it triggered the huge effort
the next generation
that actually succeeded.
I was fortunate enough to visit because there were two LIGO experiments, one in Louisiana and the other one is in
Hanford,
Washington.
You're looking for an effect that is so small that you wouldn't believe it unless you see it on two independent instruments.
There you go. So you've got these pathways.
4 kilometers
long. 4 kilometers long. Evacuated. You send a beam of light that is split from a laser that's split. It goes these are at 90-degree angles, and they go to the end. They get reflected back, and you rejoin them, and you want to see if their waves line up. And if they line up, then each direction is identical. You can go home. If they're slightly different, then one of these legs experienced a different encounter with the fabric of the space-time continuum than the other did.
So
that's audacious.
So actually what you want to do is you make them slightly different in the first place, but then, so that means you send your laser light in from this direction. There's a beam splitter where the light gets split in two to go down the two arms. So the laser light goes in like that. There's this beam splitter, so the light gets split in two into one arm in that direction, the other arm in this direction. And then it comes back and recombines in the beam splitter. The laser light was coming in from this direction, but when it recombines, a little bit of light goes out in a perpendicular direction. So you have a laser here and you have an output over there. And the output direction is the direction that has a signal. And if the if the length of one arm is shortened and the length of the other arm is lengthened.
And that would only happen because a gravitational wave washed over that arm.
That's right. Then you get a change in how much light is coming out to the output.
All right. So you're trying to find a length difference. And if I remember the materials from the press releases, that is equivalent to 1/10 the diameter of a proton?
No, it's equivalent to, it's 10 million times smaller than an atom and 100 times smaller than a proton. 1/100th
the diameter of a proton. Meanwhile, all the world is vibrating because everything is at a temperature. And cool it as much as you want, there's still vibrations. And somebody is walking down the street. I remember being on campus there. Can I call it a campus? That's what it was. And you can detect cars on the road a mile away. You have to insulate this. That's half the science done for the experiment. You should get a Nobel Prize for that.
The way I like to describe it is you're bouncing light off of these mirrors, and you're looking for a motion of the mirrors that is 10 million times smaller than the atoms of which the mirrors are made. The atoms in the mirrors themselves are vibrating because they're at finite temperature by an amount that is about the same as their size. So 10 million times smaller than the atoms, and 10 million times smaller than the vibrations the atoms are undergoing.
So once again, in physics, there's a phenomenon we're trying to measure, but it's kind of buried, and you need a way to get to it. And it seems like half, if not more than half of the effort is how brilliant is your engineer that you've brought onto the task to accomplish this. How good are your tools? It's not just the idea. It's now you got to make the damn measurement. And it's not obvious. You need very talented people assembled for this.
Absolutely. And so that was the issue, is how good a team can you put together? So when I learned of Ray Weiss's idea, and I knew roughly how strong the strongest gravitational waves would be, I knew already then that it would be necessary to...
This would be the collision of two black holes.
Collision of two black holes.
And you can't just summon that up. There has to be real things in the universe that might produce that.
That's right.
You can't just wish for it.
But based on what we knew about the universe at the time, I was estimating a wave strength that was roughly correct. And it was at that level that you would have to monitor the motion of these mirrors at 10 million times smaller than the atoms in the mirrors. And I thought to myself, that's crazy. So in this book, which was published in 1973, we went to press just after Ray Weiss wrote his seminal paper. I had not yet really studied that paper fully, but I just knew that this was crazy. And so it describes in a few words Ray's idea in here. But that was the central issue. If we worked for a few decades, did we have a shot at success? In 1973, I thought, no way. But by 1975, I had turned around. I'd had long conversations with Ray. I'd had long conversations with Vladimir Brzezinski, a colleague in Moscow. I'd done lots of calculations of my own. And I came to the conclusion that you had a real shot at success if you put together a superbly strong team and you worked at it for a few decades.
And you need money, and you were well supported, I think, by the National Science Foundation.
Well, not yet. So at that point, NSF had given Ray $60,000 to get started. And
$60,000.
That's how much he had in the 1970s from the National Science Foundation. He also had some money from the Air Force Office of Scientific Research. I'm not sure how much he had, or he'd had that until in the Vietnam era, they stopped supporting science due to something called the Mansfield Amendment, American politics. And that's when NSF picked him up and gave him $60,000. that was a drop in the bucket compared to what was needed. And NSF wasn't about ready to put big money in.
This required some members of your team to like appear in front of Congress to defend this.
That's correct. And
Okay.
But that was much later. The issue was getting started. And so how did we get started? Caltech is a very different kind of an institution than any other I've ever dealt with. At Caltech, I was able to propose to my colleagues that we get into this field, that we build a experimental program in parallel with Ray Weiss's program at MIT. So the chair of the Division of Physics, Mathematics, and Astronomy at Caltech set up a committee to look at it. Committee looked at it for about 6 months, detailed study, came back and enthusiastic, said, let's go ahead. And so Caltech put private money, about $2 million of its own private money to get started. And that inflates to about $12 million today of private money when nobody else is putting anything in.
No, you're right. Very different culture
and
at Caltech,
and
as you
once
described.
that had happened, and we had brought Ron Drever from Scotland to start the experimental effort, then NSF stood up and took notice. They did their own study of this and came up with the same conclusion. And they started funding us and Ray Weiss, and it became a Caltech-MIT collaboration.
Let's fast forward to 2016, where you make the first detection.
We announced it in 16.
You announced it in 16. By the way, I would later learn that when I visited the facility in Louisiana, you already had made the detection. And people were totally zip-mouthed. I swear I didn't know about it until the press release came.
Yeah, we were all sworn to secrecy.
Yes. And so the confirmation of a first detection came from the second facility built in Hanford. And at that point, you have a time delay because gravitational waves move at the speed of light, correct? So, and Earth is a finite size. And so all that worked out.
Yeah. And so it was just 7 milliseconds, 7/1000 of a second time difference, because the waves came up from the south. They entered the Earth around the tip of the Antarctic Peninsula, traveled through the Earth, came up through the Earth in Louisiana first, and in Washington State second, 7 milliseconds later. And then the waves were unaffected by all the matter of the Earth.
So what impresses me greatly is here we have a prediction made by Albert Einstein when in 1916 or 15, whatever. Albert Einstein, in a little known fact, I mean, physicists know this, but I don't think the public knows, Einstein laid out the equations for the stimulated emission of radiation, which is the physical foundation of a laser.
Yeah.
That's it. He wrote that down first.
Yep.
And a laser would take a few decades to actually be built into the 1950s. And I'm just saying, here's Einstein predicting gravitational waves, laying the foundation for a laser, and 100 years later, his gravitational waves are found with lasers. These are crumbs spilling off his plate. And lo and behold, nobody's surprised, the Nobel Prize goes to this project. And you, along with Ray Weiss and Barry Barish, share the Nobel Prize. What year was that? 2017.
Yeah. So they apologized to us that they didn't give us in 16 because we didn't announce it until past their deadline for
well, plus
nominations.
they delay anyway. They're never.
Yeah, they said it obviously. It was obvious the prize was going for this. It was just obvious.
Yeah. You can't be a general relativity Einstein guy without being a black hole guy. So forgive me for asking you to retell a story you've probably told 1,000 times. But there's some famous bet you made. Was it with Preskell, with some other physicist?
Preskell and Hawking.
And Stephen Hawking. By the way, I was at the University of Texas when Preskell was there. I think he was like a postdoc or he was just starting out. You made a bet, and let me see if I can set the table here. A black hole, once we all agree that they exist, we can ask other questions. When you have something outside the black hole and it falls in, what happens to that information that was contained in that object? Is it gone forever? And is that okay? because information theory was a whole branch of science, shall I call it science, that was rising up at around the same time, and entropy became a buzzword among many. So what was the bet, and how was it ultimately resolved?
So the bet was between Stephen Hawking and me on one side, and John Preskill on the other side. And it was over whether or not information does get lost in black holes. The background of
why is that so bad?
It's bad because the fundamental laws of quantum mechanics, as they are normally formulated, physicists are widely agreed that quantum physics is fundamental and that quantum physics underlies all of physics.
It's the most successful theory ever put forth of the universe.
And classical physics, where there are not these quantum fluctuations, there are not these probabilities, that arises from quantum physics as an approximation under ordinary everyday circumstances.
There are many people who caricature science, physics in particular, by saying, well, we used to think classical physics was it, but now we discard it in favor of quantum physics. But that's not true. No, quantum physics absorbed, as well as relativity, general relativity, absorbing Newtonian gravity.
Yeah,
it's not discarded. It's a bigger understanding, a deeper understanding.
Right.
Okay. Just want to emphasize that.
That's right.
Many people get that confused.
And so quantum physics is normally formulated, is almost universally viewed, has built right into it from the very beginning the fact that information cannot be lost. Now, these words, information cannot be lost, are a translation into everyday language of something else, which is not everyday language, which says that the evolution of everything in the universe is unitary. And so those are buzzwords that are not part of the normal lexicon. But I want to say that to indicate that there's some very, very extremely precise version of this, of which information is being lost, is a colloquial way of saying it.
Okay. But it would represent a violation of some fundamental tenets of quantum theory.
That's right. Stephen Hawking, back when he was visiting Caltech in 1974, 75, he spent a year in my research group at Caltech. We were very close friends. And during that period, he, having discovered something called Hawking radiation, which is a very slow evaporation of a black hole. It emits radiation and slowly evaporates. He then, while he was here, began to look much more deeply at quantum theory and black holes. And he came up with a prediction that information really is lost. And when black holes evaporate, you could form a black hole. If you waited long enough, much longer than the age of the universe for normal black holes, the black hole would evaporate and all the information that went into the black hole would be gone. The black hole would be gone. You just simply lost the information. It no longer is there. And that was complete violation of the normal tenets of quantum mechanics. And yet he was claiming that that was true. He wrote a paper on this with all the technical details. He couldn't get it published. Because it was so obvious. It had to be wrong, but nobody could see anything wrong in his calculation. And so he had to fight for more than a year to get it published. If you look at this paper, you see the submission date.
As all research papers give you. Yes.
Yeah, they give you a submission date, and then you usually have a revised date, and then it's published. He fought for a whole year, more than a year, to get this thing published. And physicists struggled with this ever since. So those of us whose roots are in relativity tended to believe Hawking. And so Hawking and I made this bet with Preskill, whose roots were in quantum physics.
And he's the junior of you both.
So we made this bet. And And this was in a period when Hawking was starting to visit Caltech for typically 3 to 6 weeks every year.
Was he yet wheelchair bound?
Yeah, he was wheelchair bound going way back to about 1970.
Okay.
And this is 1990.
Oh, much
So
later. Okay.
We made the bet around 1990.
So the stage is set. Okay. The cage match is set. You and Stephen Hawking, titans in your field, in your subject, conclude, yeah, information is lost. Especially if Hawking radiation, you can evaporate the black hole and everything is gone. There's no memory of what was there. Preskel is declaring that information is not lost, and his roots are deep in quantum physics, which we know has never been shown to be wrong.
Both know a lot more about quantum physics than I do, because we'll return to this, but let me just explain that through my whole career, I've thought that the quantum gravity, combining general relativity with quantum physics, was the most important area of physics of all. But I also made a decision when I was very young, I will never work in quantum gravity because the field is too crowded. There are too many smart people there. So they have now agreed that information is not lost.
So Hawking conceded, and by association with you, or are you still a holdout on this?
No, I'm still a holdout.
Okay. And what led to this concession, if I understand correctly?
So Stephen, together with a student, was working on a idea for how the information might be recovered. In quantum physics, if you form a black hole and then it evaporates, there's also a tiny probability the black hole never formed in the first place, and the information sneaks out through the route where it didn't form in the first place. But it's not obvious that it's right. But it's conceivable that this is what
about
happened.
the idea? So maybe I've misunderstood. So I got to go back to see where I've said this even publicly. I thought as the black hole evaporates, because the energy, the gravitational energy in the vicinity of a black hole can spontaneously make a pair of particles. And one particle escapes, the other one falls into the black hole. And this just keeps going until there's no black hole left. But the particle that escapes, if you inventory those particles, they're real particles. And don't you recover all the particles that went in the first place?
Well, you recover all the energy.
But
they don't recover.
But not the inventory of particles, the quarks.
You don't get the same particles necessarily.
Okay, then I misunderstood that. I've been wrong. I think I've been wrong. I thought you get particle for particle, they come out, which blew my mind.
I don't think there's no proof that that's the case.
Well, of course. Okay, so you guys lost the bet.
Well, no.
Hawking concedes the bet.
Hawking concedes the bet.
And what was at stake for this?
The loser will give the winner an encyclopedia filled with information. Stephen Hawking conceded the bet at a big international conference on general relativity and gravitation in Dublin, Ireland, in early 2000. There were rumors that he was going to concede. And so there was a big ceremony. I didn't concede for a peculiar reason, that there is an alternative formulation of quantum mechanics in which information could be lost. It's due to Feynman, called a sum over histories formulation. As I say, I don't work in quantum theory in any deep sort of way. I do in terms of quantum technology, which we needed for LIGO, but that's a separate story. But two of the very deepest physicists working in quantum theory of my lifetime were Murray Gell-Mann and Jim Hartle. Jim Hartle at Santa Barbara, Gell-Mann at Caltech, and then he moved to the Santa Fe Institute.
Gell-Mann is credited with proposing quarks the fundamental particle of...
The giants of theoretical physics when I was a young physicist at Caltech were Gell-Mann and Feynman. And two colleagues of mine that I enormously respect. So Gell-Mann and Hartle took Feynman's path integral or sum over histories approach to quantum mechanics, and they developed it further in a form that they could apply it to cosmology, to the universe. Hartle has used that to study quantum cosmology, the quantum mechanical description of how the birth of the universe and how it has evolved. That particular approach to quantum mechanics, Hartle took it and he showed how that approach can deal perfectly well with information loss. And it deals with it. It arises because of what we call closed time-like curves. There's a certain probability for backward time travel in quantum physics. In this Feynman-Gell-Mann-Hartle approach, there's a certain probability for backward time travel. And if you can have backward time travel at the quantum level, then you lose information. That was the version that Feynman that Hartle and Gell-Mann needed in order to do the quantum mechanics of the entire universe and the birth of the universe. So that we're getting into this issue of the birth of the universe and quantum gravity here. And I am rather enamored of this approach, although I don't do it. I just look on the sidelines and admire these people who are smarter than I am and who have the courage to work in a crowded field. But I'm just so impressed with this. And with the fact that within that formulation, you can lose information.
Is that the start of a formulation that will one day marry general relativity and quantum physics?
It does do that. It's not. It's knocking
on the door.
It's knocking on the door.
Remind me now, you're Professor Thorne in this question. What is the problem with general relativity not melding together with quantum physics? What is the real holdup there?
Well, the real holdup is that they are logically incompatible with each other, and so something has to give.
And that's because of the general relativity requires space to be a continuous.
You have a continuum space, and it's a very definite space. It's not a space where you have a certain probability that space is warped in this way and another probability is warped in that way.
In fact, there are no probabilities at all.
Yeah, there are classical probabilities, but not quantum probabilities.
And so at the smallest scale, they're incompatible.
The smallest scale, they're incompatible in any place where gravity becomes extremely strong. They're incompatible. So the smallest scale, they're incompatible even here in this room. They're incompatible in the birth of the universe when gravity was extremely strong. They're incompatible in the core of a black hole where gravity is extremely strong. They're incompatible if you try to make a time machine. Hockey and I, independently with our students, sort of identified a process whereby if a very advanced civilization tries to make a time machine, it will quite possibly explode at the moment you try to turn it on. That's also controlled by these laws of quantum gravity.
So that's why we haven't seen any time travelers yet. What you're saying is Einstein puts forth the general theory of relativity, which is so successful in so many realms, and it picked up where Newtonian gravity failed, yet we must confess or concede that there's a limit to how far general relativity goes, although we've yet to find a limit to quantum physics. So the betting pool will say general relativity is going to succumb to quantum physics in some way.
Yeah, that's one way to say it. Certainly there is this incompatibility between the two.
And string theorists are trying to be they're like performing the shotgun wedding between the two branches of physics somehow.
Yeah, and I do think, again, looking in from the outside, since I've chosen not to work in this field, that string theory is likely to be a successful route into the correct laws of quantum gravity. Yeah, but they've been at it
for 50 years. Einstein went from special relativity to general relativity in 10 years. Kepler went from weird nested solids to the Kepler's 3 laws of motion in 10 years. And that's lone scientists.
We've been working to try to do controlled fusion
for 50 years.
More than 50 years. Yeah. LIGO took 50 years from the time I first started working on gravitational waves until we succeeded. It was 50 years. Okay. Some things take a long time.
Yeah, but LIGO is a machine. The merging of quantum physics and general relativity are ideas. Could it be? And I've said this. I said to Brian Greene, I said, Brian, you've been working on string theory for decades. Maybe all of you are just too stupid to figure it out, and we're waiting for someone else to be born into this field to then solve it in the ways none of the rest of you can. None of them are saying, I'm too stupid to figure this out. Let me choose another profession. No, they're saying the problem is too hard. And if you go 40 years of really smart people not figuring something out, that tells me either they're barking up the wrong tree or none of them are smart enough.
I think you have to remember that we do build on each other.
Yeah.
None of them by themselves are smart enough.
Okay.
But the community, again, it's like this Nobel Prize really belongs to 1,000 people. It doesn't belong to me. Newton spoke of standing on the shoulders of giants, and that really is true.
If I can see farther than others, it's because I've stood on the shoulders of giants who have come before me.
And that's the nature of science. And the struggles that our colleagues have been having with string theory and M theory and quantum gravity, we've learned an enormous amount. It shows it's very promising, but it's going to continue on into the next generation before the ultimate success is had, very, very probably.
So you're 84. You have 84 years of wisdom coursing in your veins and arteries. Are there any projects you're working on in the next several years?
So I made a gradual transition, conscious, away from science, away from scientific research, beginning around 15 years ago. I would like to believe I can live to 110. That's my intended goal. And so for the next remaining decades, I wanted to do things that I really enjoyed. And I've enjoyed science. I've been a conventional Caltech professor for half a century. Enormously enjoyed it. Enormously enjoyed working with students. I trained over 50 PhD students and who did far more important research than I did. Been there, done that. I have worked in all these areas of science and I've had enormous fun, but I've turned them over to the younger generation and they're smarter than I am. I decided that I would like to spend a few decades doing creative work at the interface between science and the arts.
Oh.
So Interstellar is an example.
That was going to be released in September, and then they delayed it to the holiday season in December.
So the re-release of Interstellar.
The re-release to December 2024.
That's right. That's right. That was enormously enjoyable. I learned how great it can be to collaborate with somebody as brilliant and as completely different than I am, Christopher Nolan. So my most recent collaboration has been a book of poetry and paintings with Leah Halloran about the warped side of the universe. My poetry, my attempts at poetry and her paintings, but just trying to see whether it's possible by tightly integrating paintings with verse to convey the essence of issues in science, the spirit, the essential features without conveying the precise details. No, that's not the right genre for precise details. But
by the way, I've always felt that way about Van Gogh's Starry Night.
Yes.
Where you look at that painting and you say, this is clearly not what he saw, but it's definitely what he felt.
Yes. Yes.
And you get to experience the universe through his own lens.
Yes.
And so I've always appreciated art when it plays that role.
Yeah. I have a second movie that's been in the works. It's just something that I started with Stephen Hawking and Linda Oak. That movie might never get made. I'm not going to tell you what it's about, aside from the fact that it's sci-fi. I may try turning it into a novel. I've never tried to write a novel. I don't know whether I can, but it would be fun to try. And actually, the thing that I have put almost a large fraction of my effort in, the lion's share of my effort in since the beginning of the pandemic, is a history of the LIGO project, the LIGO Gravitational Wave Project, because that is, I think, pretty clearly the technically most difficult thing that's ever been done by physicists.
By anybody?
Yeah, probably by anybody. And
1/100th the diameter of a proton, that's anybody.
Success required both developing amazing technology, new technologies. It required developing computer simulations of colliding black holes, required developing quantum precision measurement technology that is now in LIGO and is playing a major role, where you circumvent what's called the Heisenberg uncertainty principle.
My mind is still partly blown by you having said that. You're bypassing Heisenberg's uncertainty principle.
Yeah, that's right. By manipulating vacuum fluctuations, just like advanced civilizations
might do as a routine thing.
Yeah. So we developed this new area of technology for LIGO. But it was also a very political thing. How do you get $1 billion of taxpayer money for a field that didn't exist when you began?
And should they bet on you and not someone else?
That's right.
And plus, I think you even had naysayers, if I remember correctly.
Yeah, yes.
Colleagues would say, "This is a pipe dream."
We had political battles in Washington.
Yeah. Tell me who the naysayers were.
Some of the leading astronomers. They've come around because this is so exciting now that LIGO succeeded. But the sociology of the transition from small science to big science is a very rocky process.
And that's the right word, sociology, because that's what it is.
I don't like working in a big science project. It's not for me. Just like working in a crowded field is not for me. But we had to this had to make the
it wouldn't have happened otherwise.
Transformation wouldn't have happened otherwise. And the genius of Barry Barish in making that happen was, and the genius of Robbie Vogt in getting us partway there. The very beginning is our initial director, who was the one that sold it to Congress and it really got us going. It's a very complicated story, and I have 5 collaborators that I've been working on with this history. We just finished draft 6 and sent it out to LIGO colleagues to comment on, and I have getting back huge numbers of comments. So anyway, this history, because of the nature of this project, it's a very interesting and complex history that is quite important for the history of science.
Especially when you consider most people knew nothing of LIGO until they see the headline that it discovered gravitational waves. Right. And why would they have any thought of what challenges preceded that? No. They just read the result. Oh, scientists discover this. Well, how about the like you said, the politics, the sociology, the genesis, the who's standing on whose shoulders, who are the naysayers, all that has to be overcome.
The international collaboration, key input from the Soviet Union in the depths of the Cold War. It's just a fascinating story.
You know what Arthur C. Clarke said? He said, in space where there is no air, a flag will not wave. So maybe the universe is not a place where we should be waving flags. Collaboration is what gets you there.
I like that.
So, Kip, this has been a delight. Thanks for making time.
A lot of fun.
For StarTalk. I look forward to the re-release of Interstellar. We're recording this before that has come out. And you already know this, but let me reaffirm that film just took people on a ride far beyond anything they had imagined. It had a kind of an impact on people in the way 2001: A Space Odyssey did. It was mysterious, it was modern, it was the future, but it was still relevant. But it left you with more questions to ask than questions answered, and that you want that, I think.
Yeah, and that was really the genius of Christopher Nolan, taking some science that he and I had put together, but combining it with a human story that it was powerful.
And with marquee director and marquee actors that made sure it would get noticed.
And music.
I'm going to give it another listen, because there is no 2001 without its musical track, with the Strauss waltzes,
but this is very different. I mean, it's all Zimmer's original music, and it's a remarkable score.
I look forward to your next 25 years, dude.
Okay, thanks a lot.
Thanks.
Great to see you again.
Thanks. This has been a special conversation, exclusive one-on-one between StarTalk and Kip Thorne. Today's topic, infinity, with my friend and fellow physicist, Stephon Alexander. We'll get to him in a moment. Let me introduce my co-host, Negin Prasad. Negin, it's been so long. You are a host of the show Fake the Nation?
That's right.
Well, help me welcome my friend and colleague, Stephon Alexander. Stephon, you're a returning guest. You first appeared with us when we were on the Nat Geo channel. And it was a Nat Geo TV episode. You're a theoretical physicist, a cosmologist, a musician, and an author and professor of physics at Brown University up in Providence, Rhode Island. And among those books, the one I remember most is from now 7 years ago, The Jazz of Physics. Let me get the right subtitle here. The Secret Link Between Music and the Structure of the Universe. And then you follow that up with Fear of a Black Universe, an outsider's guide to the future of physics. So you're still at it, but you're also a jazz saxophonist? So you're out of control here, it seems. You also appeared in the 2022 Netflix documentary, A Trip to Infinity, and that is the subject of today, infinity, which boggles everybody's mind who's ever thought about it. And so could you just tell us what infinity... Wait, can I tell you my first encounter with infinity? So I am 5 when Kennedy is assassinated. Okay, that's how old I am. And there's the burial, and they put him in Arlington Cemetery. And there's a flame there at the burial spot. And they called it the eternal flame. And I said, what? And then I would later learn, yes, that is figurative, that it's eternal, but there is a formal mathematical concept called infinity. So, Stephon, tell me about infinity. What's up with that?
Let me admit something to you and again. I don't know what infinity is. I think my first encounter with infinity was just as a kid. Like, you get taught how to count, and you say, okay, let me count. 1, 2, 3. And you realize that you could just go on counting for eternity. And, at some point, I think it was a friend or a teacher, I forget, I was in 3rd grade, who said, actually, there's this number. It's called infinity. And so basically, once you get to the largest possible number, you can continue counting. And infinity is that number that goes on, basically, and of course, to what? To infinity.
And plus, the old geek contest is what's the biggest number you can name? Then you name it and say, is that +1? And that's how you win. You
right.
win the geek counting contest. Yeah,
exactly. And then, of course, there's I think the other one. I want to say it's Zeno's paradox.
So, Stephon, what's your simplest example of Zeno's paradox?
Well, imagine you have this turtle that's trying to run 100 meters. Okay, the rule is that every time he gets halfway, he has to go half of that. So if he gets to 50 meters, he has to now run 25 meters. And once he gets to 25 meters, he has to run a half of that. And he continues successively doing that. He ends up never getting to 100 meters.
Because you can always take the remaining distance and cut it in half.
You all take the remaining distance and cut it in half. And
So
that
he'd be
remaining
doing
distance, and cut it in, yeah.
Okay, so this will just go on forever.
That just goes on forever, exactly.
Will he ever reach the 100 meter mark?
According to this rule, he will never reach 100 meter mark because he just keeps covering half of the original distance successively to the point where it ends up being a half of ends up being 1 over infinity.
Okay, and so but the turtle does go the 100 meters. So maybe that's what I guess Nagin, I guess that's why it's called a paradox.
And that's why it's a paradox. How did it get to to the 100 meter if this is a possibility?
By taking an infinite number of halvings. Yes.
Yes.
And when I was a kid, I thought, I have a solution. There's a point where you have atoms, and how you can go half the distance when there's no more thing to have. And then that is just there. That was my solution when I was a kid.
That actually is a nice solution to that paradox, by the way. Yes.
You basically reach the pixel size of space-time.
That's
and
right.
then you can't have that pixel, so you grab that pixel and you're home free. So that's it. That was my solution.
Yes. Another place where we encounter infinity is let's look at fractions, right? I have 1 over 2. Well, if you tell a kid, hey, I'm going to give you half of a slice of pizza, half of a pie of pizza, or 1/4 of a pie of pizza, right? The kid will know I want half of the pie of pizza. They know that the larger you make that fraction of the slice, right, they get a smaller slice of pizza. You're going to get 1/16 of a slice of a pizza versus, 1/4 of a slice of a pie, right? The kid knows that the larger, that 1 over whatever it is of the pizza, they're going to get a smaller piece of the pie. If you tell a kid, you're going to get 1/2 of the slice of a pie of pizza. Yeah, that's good. If I say, you get 1 over 1 of the pizza, well, a smart kid will say, I get the whole pie, 1 over 1. But now, if I say, if I go smaller than 1, which is smaller than 1 is something that looks like 0, 1 over 0, then that number goes, that's what infinity is. A number gets bigger, a fraction gets bigger and bigger and bigger, the smaller and smaller I make the bottom number, right? So that's another place where we encounter infinity.
You left out the middle part there. So if it's 1 over 1, that's a pizza, right? That's the whole pie. If it's 1 over a half,
it's 2.
That's 2 pies, right?
It's
1
2 pies.
divided by half. A half goes twice into 1.
Very
and then
good,
1 over 3, that's 3 pies.
3 pies, exactly.
I mean, 1 over a third.
Thank you very much.
Yeah.
So now if I do 1 over, like, if I keep, as you said, 1 over 1/3, 1 over 1/4, 1 over whatever. Now I go to 1 over 1 infinity, I get infinite pies, right? And that, we call that a division by 0. And so computers crash, actually, because, if Neil used to, I know that very well, I used to write code when you were an astrophysicist, when you were a research astrophysicist, because somebody told me so. And so, you wanted to avoid these kind of things when you wrote code, these divisions by 0, because what would happen, right?
Yeah, the program crashes. Yeah,
it crashes, exactly. The computer doesn't know what to do with it.
Asymptote is another one of these concepts, right?
Yeah,
it's a great word. It's a great word too.
Right, it's a fun word. You almost get there, but never quite until you go out to infinity. And that's another. In fact, that's very relevant to physics. And by the way, the ideas of the asymptote and this division by 0, all of these things, does, touch, have, a deep relationship with physics and astrophysics and cosmology.
So you're saying it shows up in a lot of different ways?
It shows up in a lot of different ways. And we, physicists, there's, of course, philosophers that pay a lot of attention to infinities. Mathematicians actually make a living from it.
It always drives me crazy when I hear that a singularity has infinite density or that the universe is infinite. Is this just something we label things that we don't fully understand?
Are we just invoking infinity because we can't otherwise solve the problem?
Yes and no. Can we evoke one of your favorite astrophysical objects, Neil?
What's
the black hole?
Sure, let's do it.
Because I think this is a very good example of where you kind of get to have your cake and eat it too. Because here it is an interesting thing. When Einstein came up with his theory of general relativity, which describes how matter and energy can warp the space-time fabric and create the effect that we call gravity, a mathematical prediction, a mathematical solution came out of that theory. This theory spat out a very extreme, sort of extreme warping of space-time from a very, basically a collapse, a star that has collapsed into a very dense region. And this thing is called a black hole. And Neil, you've done some excellent reports on that in the past.
But just to be clear, Negin, he said that Einstein's theory just spat out the equations for a black hole, but with the help of really brilliant people.
And it was literally, the Einstein's theory was 10 coupled nonlinear partial differential equations. Very, very difficult, and still difficult to solve. So you're lucky when you get one solution, and the black hole solution, or the Schwarzschild solution, named after, I think it was, was it called Schwarzschild?
Carl Schwarzschild.
Thank you.
Yeah, his nephew was Martin Schwarzschild, who was at Princeton. While I was there, actually, he had some good wisdom to share. But yeah, Carl Schwarzschild, who sadly died in the field during the First World War. So we're glad he banged out the Schwarzschild solution.
It was a majestical solution, but at that time, some people, and one of my mentors, David Finkelstein, of the Eddington-Finkelstein coordinate system, which was based on Schwarzschild's solution about the event horizon, right? The point of no return once you fall into this black hole after it gobbles you up. This was seen by many to just be some mathematical trickery, some mathematical solution that has no element of reality, until, of course, we found one. Okay,
right.
And we found many, right? Now there are black hole laboratories out there. Okay?
Yeah.
And so the thing that I find interesting about that was people already knew that the black hole, the reason why they thought it was a mathematical artifact or mathematical gobbledygook of Einstein's theory, some physicists thought, was because it actually had a singularity. it actually had an infinity. What do I mean by that? If you actually, this is the example we used before. If you look at if I fall into a black hole and if I describe going in as the radius, like a ball, think of the black hole as a gigantic ball in outer space, a gigantic invisible dark ball. And as I go in to the center of the black hole, this radius will eventually go to 0. But if I divide, and it turns out that the density and the force really falls off, it actually decreases as 1 over r, sometimes 1 over r squared, 1 over r. So what happens when r goes to 0? You get an infinity. You get an infinity in the density, the mass density.
Infinite density.
An infinite density, thank you. You get an infinity in the forces, right? And you get an infinity in the curvature, because the curvature becomes infinite as well.
So I think the person who asked the question knew that that's what you would say. How can you have anything that's infinite anything? That's a right. Physical thing. How is that even possible? We agree you can do that mathematically. No one's arguing that. Now you're going to tell me an actual physical thing hits the infinity that your math delivered.
Many people thought that's not real, but then you find this thing in reality. So what do you do with the fact that this infinity is there in the prediction? And so then this is where you get disagreements amongst physicists and astrophysicists. Some people say, well, there's something that replaces that theory, meaning general relativity. There's some new physics that we do not know. Some people say you have to accept the infinity, there's something is censoring that infinity from actually realizing itself and coming out and doing bad things in the world. Maybe this horizon, it's protecting.
I like that idea that nature might be censoring our infinities. I like that. And so fact, it could be that the infinity is the limit of the applicability of this theory of the universe. Okay, so Stephon, you were going to add to the point about the black hole singularity being an infinite density point and possibly others stepping in to save the day.
Yes. So there are other types of singularities that show up in physics that can maybe, I think, that where we were able to what we call tame or cure the singularity. And
the beast.
The beast, yes.
Tame
so
the beast.
one was the electric charge and the electric force. So if you look at a charged particle, good old charged particle.
An electron, okay.
Or a magnet, right? Mm-hmm. The magnetic force also between two magnets, actually, as I bring the magnets closer together, actually turns out that force, when you go to 0 distance, according to the equations, that work really well for all of our motors and all of our electricity and all that wind energy and all that stuff. It uses the same physics that we trust. But according to this physics, when you go here, all that good stuff goes out the window, because you get, according to the theory, an infinite force and an infinite amount of energy. And we do not measure that because the magnets touch and nothing blows up.
And you're strong enough to make the magnets touch if they're resisting each other.
That's right. You're strong enough to do that. But according to this thing, the magnets should never touch. You can never be strong enough because you require infinite force to make them touch.
All right.
But, okay, so what solved that problem? It turns out Richard Feynman and his colleagues figured out actually there's quantum physics going on. So what happens is that quantum physics fuzzifies and softens in a sense. So so weird things happen. So in the quantum world now, if you say, okay, the force between the magnets, is really what we call a non-quantum or classical theory. It doesn't require quantum things. What do I mean by quantum now? Well, it means that there are things called quanta. And in this case, the thing that becomes the quanta is light. Because light is actually the thing that's mediating, communicating the force, actually. And so what Feynman taught us is that you can't no longer think about the magnetic field as a magnetic field, but actually as a particle called a photon that gets transmitted, bouncing back and forth. And as a photon is communicating this force and the magnet gets closer and closer, the photon can actually, do weird things. It can do weird quantum
Okay, but
leaps.
The point is, you are saving the magnetic field problem invoking quantum physics.
Yes.
Is quantum physics going to save you from the center of the black hole, from the singularity?
Very good. So there are now the great physicists, that argue, like Stephen Hawking being one, and Gerard Tufte and Lenny Susskind and others, that said, what if what happened with, with real magnets, by analogy, there's something quantum. What quantum? Quantum gravity. There's something to do with gravity being having a quantum effect. What if that would like jump in and save today? And as I go into the singularity of a black hole, you don't get infinity, but you get new quantum effects. What would that look like?
You'd have to marry quantum physics with Einstein relativity for that.
You have to do that. Here's a funny thing. If gravity and quantum mechanics were to be a couple, they're very incompatible with each other. Every reconcilable difference is that disallow them from actually making a bond.
Okay.
I once heard Alex Filipenko explain infinity in our universe is operationally infinite to us because we can never achieve the edges of it, not even at the speed of light, because space is expanding faster than the speed of light, almost like going up an escalator that is going faster than you can walk up it. You'll never reach the top. Is my small mind grasping this concept of an infinite universe? And if so, or if not, how do multiple universes fit into our infinite universe?
Ooh, I'll contribute 2 parts. You take care of the rest. So, yes, if the universe is expand, and Alex Filipenko is a colleague of mine. We came up together actually in graduate school, and so if you have an infinite universe that's expanding, right, you'll never reach the edge. And I'd love, like you said, we all agree that escalator analogy is excellent. However, you don't need an infinite universe to never reach the edge. For example, the surface of the Earth is not infinite. Yet you could just keep walking and never reach the edge. So don't equate reaching an edge with something having to be infinite, because the space can turn back on itself and you can end up just making loops and never stop walking and always walk in the same direction, whichever direction you choose, and you'll never get to the edge. Just that my first point to that. And the second point is, if you embed, so I can have a sheet of paper that's infinite, okay? Now, but a sheet of paper is 2 dimensions. I can have another sheet of paper that's infinite and put them 1 centimeter apart from each other, and they will never intersect, even though they're both infinite, because I pulled one into a 3rd dimension. And so when you embed infinities in higher dimensions, you got no problems at all. You can put them in, cram as many as you want in there, and there's plenty of room.
And of course, there's infinite time. You can have a finite world, but the clock can continue ticking for an infinity. And so that's another example of meaning that the universe could be finite in extent, but just continue expanding for infinity.
To follow up on what you just said, Stephon, so if the spherical universe were expanding, you would still have a finite universe, but you could walk in it forever, even though it's expanding. So there's a lot of variations on this geometry that make for fascinating thought.
Absolutely. Yeah. And in fact, one of the great mathematicians, somebody that Neil, he went off and made a lot of money, but he literally, he put a lot of money towards this satellite so that he can, know about the Big Bang, called a Simon's Observatory.
Oh, yes.
Jim Simons, he's a geometrist, so he came up with some important mathematics all about this topic. He wants to put his bet that the universe actually is finite. It's a sphere. It has a spherical geometry, and if you play with the assumptions and the data and the statistics enough, you might be able to still accommodate that the universe actually might be finite in terms of the data. So that's an interesting side note.
And just in case people don't know, Jim Simons made his billions trading in the stock market, bringing high-level mathematics to his predictive models that no one knew was even possible at the time. And now he's put his money back to further research. There's the Simons Foundation, the Simons Center for Research in Physics, Biology, and Computing, which is right here in downtown Manhattan.
Can string theory be represented by music? If so, would it be more of a monophony, classical or jazz? Would it be a complete composition, or would it continue on into infinity?
Well, this is actually a good point to actually talk about, going back to Feynman and his colleagues, that they use quantum mechanics to smoothen out, for lack of better words, de-infinitize the infinity. That I made up a new word. And, there is now an uber quantum theory, and that theory is called string theory. And it turns out that just when you thought that quantum mechanics actually would help with infinities, it turned out that quantum mechanics itself had infinities. Okay? And we call these things divergences or instabilities. These are all words that just basically mean that things in your theory go to infinity. Okay? So anyway, it turns out
you're saying quantum physics was brought on to possibly help with the classical infinities, but then it introduces infinities of its own.
That's correct. Yes.
Okay, that ain't right. That ain't right.
Right. Ultraviolet or infrared divergences for the audience member who want to get fancy. So it turns out that string theory actually, one of the reasons why many people got behind string theory, including a younger version of myself, when I was a younger researcher, was that it actually was an infinity-free theory, quantum theory actually, that contained gravity in it as well, contained aspects of all the forces, but you had to live in 10 dimensions. Okay, now that you have all these other dimensions, you can go and stuff infinities on those other dimensions now, right? But anyway, string theory is such a theory that does that. It's a theory that does not have in its mathematical structures, and the solution it spits out, and it does not have infinities. So we all love that. It's elegant and beautiful, and it's also a musical theory. That's correct. So your member is quite right to say that string theory has a musical sense to it, and I'm happy to speak to that.
I do want to hear what you have to say about string theory and music, because that is a part of the questioner's content.
Well, So they should have just called it maybe something like guitar string theory. Maybe better. But yeah, so string theory. One of the good ways was able to solve these infinities had to do with an assumption that we made about even our physics pre-string theory, which is that things fundamentally are made up of point particles. And the minute you talk about a particle, then you're forced to go to zero, and that's when things blew up on you. The infinity revealed itself. But the idea of string theory is that nothing is ever made up of a point particle anymore. Even when you take a magnifying glass and you try to resolve that point, instead what looks like a point from really, really far away, like this thing here. Looks like a point, yeah?
Mm-hmm.
All right.
I'm faking it to look like a point.
Okay,
you zoom in and you realize it's a string. But it's not just any old string. The string, because it's quantum, has to be vibrating. And we know very well the physics of any kind of vibrating string. The vibrating string generates a spectrum, or it generates characteristics, types of waves, and these waves are called standing waves. What is a standing wave? It's basically what you know as a note, a tone, a particular type of vibration that can be represented as a sound, or a note on the piano. So like when I play a note on a piano, what's really going on is that there's a piano string hidden, and that piano string is vibrating. And because it vibrates, it undulates at a given rate. That rate of vibration, called a frequency, denotes what we call a tone or a sound. And so string theory, the physics of strings, really does match on very nicely to the physics of how notes are generated in instruments.
I was wondering, do sound waves have any mass? And if so, what is the difference in mass created by the sounds of musical instruments versus the sounds created by a computer?
Okay, well, sound waves do have mass, because actually the scientific word for a sound wave is what we call a pressure wave. So anytime like I create any sort of change in the pressure, it could be the pressure of, that's why you can hear sounds underwater. because even the water is compressing and decompressing, and that compression in the pressure, right? Higher and lower pressure. And for things to do that, they have to have mass to actually create a change in the pressure.
Well, the medium has mass.
The medium,
but does the sound have mass?
Carrier of the sound, the thing that's carrying the sound, okay, has mass, like, right? But actually, you know, you can say then it's a very deep question actually, because our perception of the sound, you know, sound is massless in that sense. but
sound has energy, and energy
has energy
equals mc squared. So there's a mass equivalent to the energy that's in the sound, I presume.
That's absolutely true. That is true.
Okay, all right. So that bails him out of that one. Yeah. Yeah. All right, Nagin, see how many more questions you can squeeze in.
Question for Dr. Alexander. Neil says, quote, "The universe is under no obligation to make sense to us. So how do the concepts of infinity and quantum mechanics get distorted due to our human condition? And how do you reconcile this gap with your research and your artistic expression through jazz music?"
My take on this is that I actually embrace the infinities. I embrace it. I said, let's live with the infinities, and wherever we can, try to sidestep it and make progress. And yeah.
I see. Okay. So you kind of, even if they're difficult, it shouldn't prevent you from making other kinds of discoveries in the terrain that surrounds them. I get it. Okay. And how about and again, the second part was about jazz.
Yeah, I mean, you know, one of the things that's great about jazz music is that, you know, it's a dual thing. You're always striving to master your craft and, you know, and build on the foundations of others, but you also must try to break the rules and stumble and fall to make something new based on that foundation. So really embracing the mistakes that you made and not being afraid of that. That's kind of what jazz improvisation is also about, while at the same time building on the foundation and getting your chops together and practicing and all that good stuff. So I used to always feel like I was the outsider physicist that played music. It turned out that the hero, the guy that won the Nobel Prize for figuring out how to actually deal with infinities and our quantum field theory that led to the discovery of the Higgs boson, his name is Ken Wilson. I just found out that he played the oboe. Like, you know, he played when he was a postdoc, yeah.
I saw that Stephon's specialty includes quantum loop gravity, and I've always wanted to ask, what the heck is quantum loop gravity?
It's a very tantalizing idea, and it actually does deal with gravitational infinities in some respects. And the idea is really interesting. You know, like how, let's go back to our picture of the magnet. You know, if you actually can see a magnetic field line with these iron filings, you see that it's like some of it is concentrated in like a tube, like a magnetic tube. Well, what loop quantum gravity is saying is that imagine that you can make tubes of gravitational fields and sort of loop them around like chains, like, you know, like a chain. But I can have like
a link in a chain, like
a link in a chain, and I can link a fabric of space-time with those loops. Like imagine you zoom into my fabric, this fabric of the show, and you start seeing it like loops and links and that kind of stuff. So that's the idea of loop quantum gravity. But what's linking is the gravitational field. And they're kind of, you can think of them as atoms of space. So, yeah, so.
Oh, I see. Not atoms, pixels of space.
Even better.
Yeah.
Even better.
Pixels
of space, yes.
The smallest unit of space. Yeah.
The smallest unit of space. And I mean, that idea, that theory is still in play. In fact, I will be seeing one of the founders of that theory, Abai Ashtekar, very soon.
And they're especially loopy. They're especially loopy.
I struggle to think about space-time as a concept that exists in our daily lives. As a medium, though, which light wave travels, as a fabric that gets shaped by mass, and as a vacuum out of which virtual particles pop in and out of, what's an easier way to think about space-time?
I think it's a good analogy to think of space-time as some sort of very, very faint and invisible fabric. But it's a special kind of fabric because that fabric can also support space-time itself to move along, like gravitational waves, right? So space-time itself can actually support motion of ripples of itself, and that is different than any other types of medium that we know, right? Normally, something like an electric field or particles need space-time to move through, but they can't move through their own medium. Space-time it's a very special type of medium in that sense. But it's a very weird medium, for lack of a better word. It's what we call it's a relational medium. Okay.
And nor is it under any obligation to make sense to us.
Again, this is what Neil just said makes no sense. But I know I could write down this object called a space-time metric, and we describe it as a field of, space-time as some kind of a field. But again, these are just words that we attach to the equations that we write down. Yeah.
But they make predictions and they work. So
they make very good predictions and they work very well. Yeah.
So that's why, however fantastical they sound, they still are connected to reality in that important way. So it's very.
The detection of gravitational waves with LIGO and Virgo. Yep.
We got to call it quits there. Stephon, great to have you back on the show.
Thanks for having me again, Neil. And it's great to meet you, Megan. I look forward to checking your stuff out.
This is special edition, which means we've got Gary O'Reilly. Gary.
Hi, Neil.
Hey. And we got Chuck Nice.
Hey.
Okay.
What's happening?
And special edition specializes in all science that matters to the human condition.
Yes.
And today's topic is no exception. May I give the title of it?
Please do.
Why we die.
Humankind has for millennia asked, why do we die? Followed by, well, why can't we live forever then? And then...
It's kind of the same question.
But aren't different people. So has evolution programmed us to expire on a certain date? Could we extend the game? Cheat death, play God, if you wish. Millions, if not billions, are spent annually on anti-aging, be it research or products.
Billions of dollars.
Yes.
Okay.
And so how close are we to unlocking the mystery of death? So no surprise that the research into proteins is proving to be the key to this mystery.
We have the world's expert on this very subject.
Wow.
And this is Venki Ramakrishnan. Venki, welcome to StarTalk.
Thank you.
Excellent. And you are now based in Cambridge.
Yes.
You run a small group, but used to be bigger because you're winding down in your career. A program leader at the MRC?
That stands for Medical Research Council.
Lab at Cambridge. Yes. And it specializes in
molecular biology.
So
it's the MRC lab of molecular biology.
Okay. In 2009, you were awarded the Chemistry Nobel Prize. Former president of the Royal Society, basically the first in the world to organize the ideas and publications of scientists.
Wow.
To make it a clearinghouse of peer review. Really.
First peer-reviewed papers. It advocated evidence-based science in the 17th century at a time when authority mattered a lot. And they said authority doesn't matter. Beauty doesn't matter. It's evidence that matters.
And then you got knighted in 2012. That's 3 years later. And did they knight with an actual sword?
Yes, but I think it's blunt.
Oh, also you have a book. It's your second book, first one a few years back, The Gene Machine. But what we're especially interested in now is Why We Die. And give me the subtitle of that book, Why We Die.
It's called The New Science of Aging and the Quest for Immortality.
Well, let's dive right in because you are our world's expert in this. And before we can define death, I guess we should kind of define life and then learn what it is that ceases in life that then brings death upon it.
Well, defining life is very hard. It's, you could almost say, quote, Justice Potter Stewart, as I can't define it, but I know it when I see it.
Spoken of, maybe you don't know.
Pornography.
Because that's America. He said that of pornography.
Okay. But the fact is, life, most biologists would define it as a system that can self-replicate and evolve. And at least in our world, it's carbon-based. But when we talk about death, it's a little complicated because there are many different kinds of death.
Oh.
You can have societies dying, cities dying, nations dying. You can have companies dying. But what we're talking about is the death of the individual, which has the
organism.
Of an individual animal or organism, right? And there's a peculiar paradox there because while you're alive, I mean, right now, millions of cells in you are dying. You don't even notice that, okay? That's cell death. They need to die in order to in order to keep you alive.
To make room for the new cells.
To make room for new cells, actually during development, cells will die at precise points during development. They've done their bit, and then they have to get out of the way.
When you say development, you mean embryonic?
Embryonic development, correct. And at the same time, when you die, when you say a person has died, at the point of death, most of you is still alive. That's why you can donate organs.
Right.
Okay.
So there's the other side of the paradox.
Interesting.
So what do we mean by death?
You're right.
Okay. You can have, by the way, since you're an astrophysicist, you can have death of the universe as well. And there's a book coming out on that, or has come out. So the question is, what do we mean when an individual dies? What we mean is the irreversible loss of that individual's ability to function as a coherent whole. So that means that person can no longer exist as a unit. And that's what we mean by death.
Are you talking physiologically this person cannot function as a unit? Because there are people who experience brain death to an extent, and they keep them on a respirator because a family member says, I don't want them to die.
So there are two examples coming out of Chuck's point. You can be brain dead, but sustained on a respirator, so all your organs are working, or you can be body dead, I suppose.
What you said can't happen, because if your body's dead, then it can't feed nutrients to the brain to keep it alive. The brain is the biggest consumer of
resources.
Resources in the body. So coming back to your point, though, about brain death, et cetera, that's interesting, because it used to be that if your heart stopped beating, that was the moment people said you're dead.
Right.
Then they found out that actually, even if your heart stops beating, they can resuscitate you.
Right.
But then they decided, okay, when you no longer have brain waves and your brain has irreversibly stopped, that's brain death. And there's an interesting case. States in the U.S. used to have different definitions of death. And there was a case where somebody died in California, but her relatives wouldn't accept it. And by New Jersey laws, she was not dead. So they moved the body to New Jersey.
Oh, wow.
And she was maintained, as you say, on some sort of artificial device. Right. And then eventually she died. But this is slightly getting semantic, because most people agree that there's a point when the body cannot reverse itself and get back to being alive.
Yeah, but that's a statement of the limits of medicine in the day.
Today.
Right.
Correct.
So I read this, that one of the definitions of death is if you do not fog a mirror held up to your mouth.
Yeah.
However real our current definitions feel about when someone dies could be modified in the near or distant future.
Absolutely. And neither birth nor death are very clearly defined. And I've pointed this out, that they're both somewhat fuzzy. I mean, when is it that you actually are you at birth? And that's the whole argument about abortion and all of that is just about that. And similarly, the point of death is also
when are you
a
no
little
longer
fuzzy.
you? Yeah.
So the bit in between is aging.
The bit in between is aging. And you start aging even in utero.
Interesting. Wow.
From the time you're conceived.
Forgive me, as an astrophysicist, I hear talk of cells but then I also hear talk of proteins. So could you distinguish the two of them for me with regard to the role of aging?
So aging you can think of aging as an accumulation of damage and changes to our molecules, our cells, our tissue, and entire organs and the body. And this aging occurs at every one of those levels. So if you think of the molecule that holds all the information necessary to make all of the other molecules in the cell, that's our genes, our DNA. So DNA can be damaged. It can also change, which is not exactly damaged, but it can be modified as we age, typically by adding chemical groups to it, often methyl groups.
It's gene editing.
It's epigenetics.
Yes.
It's not editing as such. It's not changing the bases. It's not changing the letters of the DNA.
That would be gene editing.
That would be gene editing.
Okay.
This is epigenetics, which means sort of on top of genetics.
Like the epicenter of an earthquake is the point on our surface above where the...
Right.
Yeah.
And so you can modify DNA, and that changes the way in which the program is expressed. So which genes are translated into protein.
So this is the
and
playing
which
God
aren't.
part, because now you are changing the
No, we're not
that
doing
just
anything.
happens.
This
So-
is happening.
Yeah.
This is
Okay.
happening even in utero.
Experiential circumstances can change your epigenetics.
Is this the
So it's part
translational
of-
control of
It's
proteins?
just part of life. And it evolved for probably a very good reason. Mainly, it may have been a cancer prevention mechanism early in life. We can get into why we have death from an evolutionary point of view. But nevertheless, the DNA program itself ages. Damage and modifications change the nature of the genes that you're expressing. Then that results in the proteins, which are encoded by DNA.
there you go.
These are the workhorses of the cell. They carry out all the function. They give the cell its structure. Almost everything you think of as a property of life, like vision or touch or antibodies, they're all proteins, and they're all encoded by DNA. But as we get older, the quality of the proteins deteriorates. They're not made at the right time and the right amount. They start aggregating. Alzheimer's is a case where proteins clump up together and form tangles.
the brain,
So that also, in the brain. So that also is a consequence of age. And as a result, things in the cell, larger entities like compartments in the cell, also start to age. One of them are mitochondria, mitochondria were actually bacteria that were swallowed up by a larger cell 2 billion years ago and then lived in symbiosis. And now, today, mitochondria are specialized as the centers for energy metabolism. It's where oxygen is used to burn sugar effectively and get energy out of it.
So it's that kind of chemistry going that far back that accounts for our genetic similarity to life forms that are nothing like us. Like we're something like 25% identical genes to a banana.
Yes. All eukaryotes came out of that.
Yes.
Out of that symbiosis.
Okay.
And so you can think of this as an ancient, organelle that's now specialized. And because it's a center for oxygen usage, it can create what are called free radicals or reactive oxygen species, because these are partially reduced oxygen atoms which are chemically very reactive. So you can have a lot of damage.
So to be clear, if it's fully reduced, that means all the oxygen is where it could
becomes
fit.
water.
And then there's nothing else that can
Carbon
happen to it.
dioxide and water is what you get.
Yes, it's fully reduced. Partially, it's basically activated
It's activated.
to
Correct.
do things.
and it does
chemically.
damage.
Yeah.
Yeah.
And so it can cause damage. And mitochondria have preserved a little bit of their own genome. They used to have a much larger genome when they were bacteria, but now that genome is shrunk. In humans, they only encode 13 protein genes, but they're essential for the function of mitochondria. And the mechanism to replicate that DNA, to copy that DNA as mitochondria divide, it's not as accurate as the mechanism for our own DNA replication. The more errors creep in. And so mitochondrial aging is a big problem with our aging.
Is that the single point of failure in terms of
It's
the
not
aging?
a single point. I think aging, I do like to say that the reason my grandson has a lot more energy than I do is because he has much better mitochondria than I do.
So this reduced chemistry that makes it chemically active, that could not have been useful before Earth's atmosphere became oxygen rich. So cyanobacteria basically turned a carbon dioxide atmosphere into one that had a presence of oxygen. And then anything that needs oxygen can
thrive.
Can now thrive. But it couldn't before then.
That's
So that helps age date, or time date, I should say. So
It's
that
about 2 billion years.
that helps time date these activities. Yeah.
So there's something called senescent cells where they age and they secrete these sort of inflammatory compounds.
So senescent cells are another, I said you can have aging at every level.
Yes.
And aging at a cellular level is often due to senescence. And senescence is interesting. It may have evolved originally as a anti-cancer mechanism or as a mechanism to get rid of defective cells.
Yeah.
So what happens is if a cell gets DNA damage, it has a number of enzymes to repair the damage, to sense and repair the damage. But if the damage is too extensive, then it triggers pathways to either kill the cell, commit suicide, or to send it into this state called senescence.
Yeah.
That can also happen, due to other kinds of stresses. And what senescent cells do is they no longer function normally and they no longer divide, but they secrete inflammatory compounds. And the purpose is to signal to the immune system that there's something wrong here, and come and repair the damage around the site. Maybe it's a wound or an infection or something.
They call the cavalry.
And call the cavalry.
So it has utility.
It has utility early in life.
Until it doesn't.
But later in life, you get too many of these events. Build-up of senescent cells, systemic inflammation, which causes organ damage, more senescence. And so it's a big problem in aging.
Yeah, and that's why you see so many medical reports now that talk about the dangers of inflammation.
Absolutely.
Totally. Like, it doesn't make a difference what kind of inflammation. The idea is to eliminate inflammation as much as you can, no matter what.
Sure. And actually, people know, for example, in the COVID pandemic, the cause of death is often triggered by inflammation, not by necessarily directly by the virus.
By the virus
It's
itself.
our reaction
So
to
it's
the
the reaction. So it's the cytokine storm that was created as a reaction to the virus itself.
Cytokine?
Cytokine.
Please explain.
The cytokines are what's released when we respond to what our body thinks is an attack on us. And
Goes into overdrive.
And sometimes it goes in overdrive.
it goes in overdrive. And,
Are we anywhere close to being, or is this the epigenetics thing where we can deal with these senescent cells?
No, but there is a new field emerging, which is cellular reprogramming. To explain that, if you start from a single fertilized egg, it divides into many cells, becomes something called a blastula, and then, or a blastocyst, and then it divides further and further, and then forms specialized stem cells, and each of those specialized stem cells give rise to certain kinds of tissues.
Yes.
right.
Okay, so some stem cells will only generate cells of the blood system, including white blood cells, red blood cells, and so on. That used to be thought of as unidirectional. You can't go backwards. You can't go back from a skin cell back to a fertilized egg or an early embryo. But that turned out not to be true. Okay, and it was done in a natural way when Dolly the sheep was cloned, but actually even earlier when John Gurdon cloned the skin cell of a frog and cloned an entirely new animal from it.
Wow.
And that meant that somehow these marks on the DNA had been erased or changed.
Just historically, that completely changed the public dialogue about our source of stem cells.
Right.
Because we only were getting them from aborted fetuses.
blood,
From fetuses.
From
right.
fetuses.
From fetuses.
Yeah.
And so that was a complicated ethical issue for many people.
Right.
And then once that blew open that whole field.
Right. Well, that wasn't Gurdon and Dolly the sheep and others, but it was actually Shinya Yamanaka, a Japanese scientist, who showed that if you were to introduce just 4 factors, these are genes for proteins that regulate other genes.
Gotcha.
If you were able to introduce those 4 factors, you could take a fully differentiated cell, like a skin cell or a liver cell or a heart cell, and you could make it go backwards in development all the way back to what's called a pluripotent stem cell. Pluripotent means it can make any tissue.
Right.
And so that eliminated the need for what you said. Which
Did he
is
not win a Nobel for that as well?
He and
did,
John
yeah.
Gurdon shared a Nobel Prize. And here's an interesting thing. John Gurdon's paper for which he won the Nobel Prize was published the year Shinya Yamanaka was born.
No.
Wow.
That's how far apart they are in age.
And all that time, all that work.
We've had sort of variations of this with David Sinclair, who we've had as a guest, took mice that were blind, cured their blindness.
Yeah.
So, I mean, I mean, if that's the case, how far are we from...
I would say it's early days.
Yeah.
Fine.
That way.
Yeah.
Okay.
I can tell you that I'm aware that this has happened, and then my question is just the distance between this and doing other things on a grander scale. Mice are one thing, larger primates are certainly another.
And curing blindness.
It's a little further down the line, is what you're saying. It's a little, but the idea is we do have. Would you say we now have not a blueprint, but maybe a template that we know we can take these programming cells and use them to maybe change our makeup?
I think the biggest use of that is in something called regenerative medicine, where if you want to replace tissue that normally can't be replaced, for example, damaged heart muscle in a heart attack, or pancreatic tissue which has been destroyed and you have diabetes, or cartilage, for example, for osteoarthritis.
Yeah, absolutely.
And maybe one day, I'm hoping even hair. So if you can do that, the regenerative medicine is a huge area of research.
Yeah.
And they're making good progress in some things.
Just to be clear, I've always been disappointed in humans for not being able to regenerate limbs the way newts do.
That's because newts have stem cells all over
their body?
All over
their whole
body.
makeup.
Yeah, it's spread out throughout, and so they can,
I'm just
or
saying,
starfish, for example.
We're old enough to remember reading biology books. Humans are the top of the evolutionary, back when we spoke that way.
It's humbling to know that we have about the same number of genes as a worm or a weed. But going back to stem cells, the thing with aging is, can you take a fully grown or an aged individual, apply these kinds of factors, and get their tissues or their stem cells to be regenerated?
Right.
Because one problem with aging is that our stem cells also age.
Right.
They decline in number and in quality. So if you were able to use a method that would somehow either rejuvenate tissue or actually regenerate stem cells, that would be a big thing. And people have done experiments to do this kind of thing in mice. And they say that the papers report that the mice look healthier, they seem younger by many criteria and so on. But how to do this safely?
And the bald mice, did they get hair?
No, but their fur looked better.
Oh, okay.
Okay, that's not bad.
So the question is, how can you do this in humans in a way that's safe, that doesn't cause cancer, that is at the right dose, and so on?
Right.
And that's a big challenge.
It
so
is.
I think it's promising, but like many of these things, the aging field, I should say, is full of hype. Okay.
Yeah.
And it's very promising, but there's a lot of work to be done before it's ready for prime time.
Are we at this sort of Frankenstein moment? I mean, you've done a Frankenstein show before with, let me get his name right, David Andrzejewicz.
Yes.
The cells you've said there can be death to the organism, but cells will remain alive. And now we've got the Yamanaka factors. Are we getting to that thing when we can create, or are we just fantasy talking here?
You mean create a new individual? Or the same individual?
Well, the same individual.
You could certainly clone yourself.
Right.
That's theoretically and practically possible. They've cloned all kinds of mammals. There's no reason why they can't clone a human being, except that all countries have decided that's a bad thing to do. But that's not the same as rejuvenating or the same individual.
Yeah. Right. Which, by the way, for selfish purposes, rejuvenation is a hell of a lot better than cloning, because that clone is not me.
People forget that.
And there's all this fantasies in the multiverse where you have an infinite number of possible molecular outcomes of all organisms. They're imagining themselves in another universe, in a way being reincarnated and living forever. It's like, no, that's a different person.
Just a different person in a different timeline.
And by the way, these transhumanists, people who think that they're going to dump their brain into a computer and then maintain their consciousness. A simple question to ask is, what if you make 2 copies of it? Which one's the real you? And you immediately have a paradox.
Absolutely.
The copies that you make will be of you of that moment, but you've in your timeline is still proceeding.
Yeah.
They would be stuck
You still
within
get to
that
go to the
particular-
beach and have friends, and your brain in a jar does not. Right.
Yeah.
I heard long ago and I checked it out, and I think it's true, that all mammals live for about the same number of heartbeats, except for humans who live 2 or 3 times that. Except if you go back far enough in time when we were just living in caves, we were right with all the rest of the mammals. Yeah. So first, is that true? Second, there are animals, not mammals, that live much longer than we do. I'm thinking of the Galapagos tortoise, for example.
Yeah.
So do you guys study other animals to get insight?
There is a whole field devoted to looking at lifespan of different species. And you are right that, at least among mammals, Jeffrey West, who's written a book called Scale, shows that the number of heartbeats is roughly the same. That has to do with the fact that smaller animals have a higher metabolic rate.
Right.
They have a faster metabolism. And they almost need to, because their surface to volume ratio is larger. They dissipate heat more.
We did a whole explainer on surface to volume ratios.
And so they need to maintain a higher metabolic rate. That's one of the reasons.
That's only one of the reasons why they have higher heart rate. That's not a reason why they should die sooner.
The why we should die sooner has an evolutionary explanation. And that is, evolution doesn't care how long you live. It only cares about fitness. Fitness in the biological sense is the likelihood that you're going to be able to successfully pass on your genes.
And people always misinterpret that as being physically fit.
Evolution cares about fitness. Now, at the same time, for most of our history, and certainly the history of all other species, resources are limiting. And so you have to select. Do you put more of your resources into maintenance and repair of the individual animal, or do you put it into growth and reproduction? There's always a balance if you have limited energy. So in the case of a mouse, which lives about 2 years in the wild, there's no sense in having a mouse live for 40 years, because long before that, it's going to be eaten.
Yep.
Exactly. Or it'll die of starvation or a drought or something. And so in the case of a mouse, evolution has favored selection of a species that grows very quickly and reproduces prolifically. That's a mouse. If you get to a large animal like a bowhead whale, let's take an even bigger than an elephant, they can live for 200-300 years, and they have a very relatively slow metabolism.
Wow.
An even slower metabolism is not a mammal, but it's still a vertebrate called the Greenland shark. 700 years. A vertebrate living for 700 years, very slow metabolism.
How do you know that?
They can do things like carbon dating.
Okay.
So you've got the mayfly lives a day.
Mayfly lives a day,
right?
Exactly.
And then between that, you've gone from there to a Greenland shark. And your Galapagos
and there are
tortoise
actually
is in
other
there.
animals that are thought not to even age biologically.
What's the immortal
like
jellyfish?
The hydra and the immortal jellyfish. And they're full of stem cells, so they're constantly regenerating themselves. But if you followed an individual, it would also age only very slowly. It's just in the wild, it dies for other reasons before actually aging.
Mm-hmm.
So there's a whole range. Now,
so humans might be the only species that dies of natural causes in the world. I mean, if you want to think about it that way.
Possibly,
We're apex predator.
Yeah.
So
yeah, I think that may be true. In fact, there's a book written by Stephen Austad called Methuselah's Zoo, where he talks about all these animals. And he talks about
Methuselah's Zoo.
So that reminds me, because Methuselah is the oldest person in the Bible,
Right.
In the
Old Testament
Bible, the oldest star we know of in our galaxy is called Methuselah.
It's called Methuselah.
Yeah.
Anyway, in this book, he points out
Methuselah's Zoo.
In Methuselah's Zoo, he points out how all these species have such different lifespans, and it's because of this evolutionary selection. But it's actually worse than that. The fact is, evolution will select for things that help you early in life, even if they cause a problem later in life. So many of the things that cause aging are related to growth, for example, or to cancer prevention, prevention of or senescent cell creation. These things all help us early in life, and they're a problem later in life. But evolution doesn't care what happens to you when later in life.
When you're not making babies.
Right.
Yeah.
Exactly.
Yeah, because that's the whole deal.
So what helps us survive in infancy and then go on to reproduction is the key component of our decline and demise.
Not always, not
Okay.
everything.
No,
But there are things that happen to us early in life that are selected for early in life that cause aging. We're an outlier. We live about twice as long as we would based on our size.
But only post-caveman life, right? Because if
Yeah,
half of
40,000 years.
Exactly. So
yeah.
half of everyone died by 30.
Yeah.
And so we're not 2x other mammals at our size. Right.
Yeah. And one last thing is there's a group of mammals, the bats. They live much longer. They're about the same size as a mouse in terms of mass.
Yeah.
They live about 10 or 20 times as long as a mouse. And the reason is they can fly around. So that means two things. They can escape predators more easily.
Yes.
Right.
And they can also forage over a much wider area for food. And when they roost in the ceilings of caves, so they're not
safe.
as accessible to predators.
They've been designed to survive longer.
And so there it's worth it for evolution to make them live longer because they'll still keep producing more babies.
If we're looking at aging, we all do it, can't help it, more or less. What have been the attempts to reverse the aging? I'm not talking potions and lotions here. So let's go through the laundry list. The sort of young blood transfusion.
Oh, yeah.
How successful has that been?
It's not incredibly successful, but the science underlying it is solid. If you connect an old rat with a young rat,
Yeah.
by that I mean you connect them so that their
transfusion.
blood systems
Yeah.
Right.
are
Sharing the
joined.
same circulation system.
Exactly. Then it turns out that the old animal benefits from the blood of the young animal, but even more so, the young animal suffers from the blood of the old animal. This means there are factors in blood that change as we age.
There's
And
such a thing as old blood.
exactly, or young blood. And that's why
Young blood.
I call it this vampire blood.
Yeah.
Wow.
So that's the science. And the research is now about finding out what these factors are, what they do. And once you know that, you might be able to figure out whether you can use them to our benefit. But people have not waited for that. What's happened is the very first time these people from Stanford, Rando and others, published this, they got creepy phone calls from rich people. Companies started sprouting up, getting blood from young donors and extracting the plasma and selling them up, at $8,000 a pint or something to, rich old people. And one of them, the FDA wanted to shut it down, and then they sprouted up under a different name. And the whole thing was like the Wild West. But there's real science under it, and that's an ongoing area.
Okay, stem cells we've kind of addressed as to how you can, through the Yamanaka factors. Calorific caloric restriction.
Yeah, so
Just basically fasting.
lots of experiments, starting in mice, but now also in flies, worms, even in single-celled animals like yeast. If you reduce the amount of calories, it turns out that you can, the animals live longer, but more importantly, older animals start resembling younger animals in terms of their physiology and their biomarkers. And so the question is, can you mimic caloric restriction? And it turns out that there are many important biochemical pathways that are affected by caloric restriction. One of them is the IGF-1 insulin growth hormone factor.
Yeah.
So it's
Wait, just to be clear, what you're saying, you wouldn't have to imitate calorie reduction. You could just consume fewer calories. We can still eat our cheeseburgers and the blueberry pie dessert, and then you hijack what would be the starvation mechanism biochemically.
exactly.
Fasting will prolong your life.
Absolutely.
So can we find a way to mimic the biochemistry of that in your body?
We can.
And the word mimic in that sentence means still eat the cheeseburger.
Right.
But do what the fasting would have done to your biochemistry.
I see what. Yes.
That's
Have your cake and eat
But you're
it.
doing it artificially, is
So
what you're saying. Okay.
in my book, I call it eating your blueberry pie and ice cream and getting the benefits of
Yes. And still getting the benefit.
One of the drugs that does this is called rapamycin. It's the darling of the anti-aging
This is the
research
Easter
community.
Island find, isn't it? Didn't it
Easter
find-
Island.
Yes.
Easter Island
Okay,
is
someone's
where it
got
was
to connect
found.
these.
Yeah,
two from here.
rapamycin. Okay, let's
So
do it. Let's-
rapamycin was found in the soil of Easter Island, from bacteria in the soil of Easter Island that produced this compound, which turns out to be an antifungal compound. And then they found out that it may have some properties against cancer. And then eventually they found out that it actually is an immunosuppressor. And that's what made it get FDA approval as an immunosuppressive drug. Then, much later, it was found in a completely different place. It was found that it shuts down a major pathway in the cell. And that pathway is related to it's a pathway that senses nutrients. So it's related to caloric restriction. People then said, okay, let's see what happens if you give rapamycin to mice and so on. And mice lived a bit longer, seemed a bit healthier. However, rapamycin is an immunosuppressive drug. So it's going to make you more prone to infections.
Being sick, like steroids.
And it has other side effects as well.
Okay.
So the question they have is, can you adjust the dosage so you get the benefits against aging without the problems of immunosuppression and so on? And that's still, jury's still out on that.
Okay, now there's also relativity where you can slow down time for yourself.
Oh, well, that's going into space, though.
Yeah, well, right.
That's one way to defeat aging, right?
However, you are still aging.
Right.
In your own body, 1 second per second.
Right.
The difference is all your friends are aging faster than you.
Much faster.
Right. So you're not going to live older than you would have as an organism.
Right.
You'll just live longer than everybody else.
Exactly.
Isn't that the
And then
Kelly?
when you return, all your friends would have been dead.
They'll be dead.
The Kelly twins, where they did the experiment
Oh,
once.
yes. We had one of them on this program.
Yes.
Scott Kelly,
Right.
astronaut who went up.
That's right.
And
his brother stayed here.
Brother stayed here. They're identical twins. And you can calculate how much younger one would have been. It's like a fraction of a second. So as you surely know in physics, we speak of this thing called entropy, where left to itself, a system will always degrade to lowest energy, highest disorder. And
The key is left to itself.
yes. So we can create any manner of complexity on Earth because we're not a closed system. We're open to the sun. So the sun is gaining entropy by helping us out. Eventually, it's going to die and nothing's going to help it.
Right.
Right. So do you guys in molecular biology think of entropy?
There's no question that entropic forces exist. But of course, living systems all use external energy to keep it alive.
Yes.
Right.
And part of the energy is used to do this maintenance and repair of the damage. But it's not perfect. And so eventually, even if you keep repairing DNA damage, repairing cells, getting rid of defective cells, all of that stuff which takes energy, it's not perfect. And eventually the system gradually decays. But it means it decays at different rates for different species.
Interesting. Or different parts, different systems, even within your own body.
Oh, that's something that very interesting. So if people were to analyze your different organs, they'd find that they all had different ages.
Yes.
To say someone's biological
Just to be
age
clear,
is a number.
different ages mean different time distance from its birth to its death.
Correct.
Right. Because obviously it's all physically the same age.
Yeah.
Physically, chronologically, it's the same age.
Yes.
Yeah.
But
Okay.
physiologically.
Physiologically, they're different
yeah.
ages.
So that's-
but it doesn't make a difference because if I got an old heart and a young pancreas, I'm still going to die.
by a heart issue.
By a heart
Yes.
issue.
So that was always what I suspected, that people who live very long, all of their organs somehow are aging at the same rate, physiologically.
Well, I don't know if that's true, but maybe they're still aging differently. But the lead organ, the organ that's aging fastest, is still slower than other people.
So given what you just said, I didn't put two and two together here until just now. In the second law of thermodynamics, one of its stipulations is if you have sort of usable energy over here and you convert it into another kind of energy over here, there's always energy losses. Always. That's why you cannot make a perpetual motion machine.
Right.
All right. And so the body is all about converting energy of one kind into another. You have chemical energy in food, and you turn it into
ATP.
Yeah, exactly. Remind us about that. We all learned it in biology class. The ATP cycle, is that right?
There's ATP is adenosine triphosphate. It's a molecule with high energy bonds. So you can think of it as a universal currency, just like in our world, electricity is the universal currency. So you use everything converted to electricity, then you can use that for everything. And so the body uses it, so you can think of it as a kind of storable form of energy that it can use.
Right, but it's taking energy from one. It's taking energy from one thing and converting
Typically,
it
in
into another thing.
in our case, we're getting it from carbohydrates.
Yes.
And by burning carbohydrates,
So it's chemical energy.
It's chemical energy.
Yeah.
So that energy is used to make ATP.
Got it. And anything else we make in our body to maintain our body temperature, because we're warm-blooded, to move. So it goes to thermal energy, kinetic energy, and the like.
And most of those things involve ATP.
And electrical energy. And,
for your brain and your heart and signaling and all that.
So I'm just saying, every time you convert from one form of energy to another, you're getting less energy than you started with.
Right.
So there is a decay in there
Yeah.
eventually.
Interesting.
And so you describe this sort of implicit value of death to a species because it doesn't need you after a certain point of your fertility. We're beyond that now, and we're what we call civilized. And so there are people who want to do anything they can
to stay alive for as long as they can.
To stay alive for as long as they can. And you're in that business scientifically. What is the ethics?
I should say, my
that?
own lab has never worked on aging. I went from zero to expert in one book. My lab works on protein synthesis, which is a central component of aging. But I don't actually do aging research myself.
Okay, but surely you've thought about the ethics of it.
Yeah.
Why wouldn't you?
Oh, definitely, yeah.
Yes.
And I also have no skin in the game, so that's...
Okay.
Chemical laws, biological laws, any in the way to stop us going from where we are now to potential immortality?
Right. So there are two issues. One is aging programmed? I mean, are we all programmed to die?
Yes.
No, because evolution doesn't care about...
It doesn't care about us dying.
So there are genes that affect aging, but those genes don't exist in order to make us age. They were selected for some other reason, but they happen to cause us to age. So now that we understand some of the biology of aging, you ask, can we extend that?
Yes.
And there are no physical or chemical laws that say that we have to die at 120. Okay? I mean, 120 is about the record for humans. Very few reach that. But there's no physical or chemical law that says, at 120,
you got to go.
You got to go. There are species, as I said, that live 700 years, vertebrates. Of course, the question is, can we change our biology to make us live much longer and still keep us humans? You don't want to be a very slow metabolic animal like a Greenland shark. You still want to be human, and you still want to live much longer. Now, there are people, I would say, at the one end of the anti-aging research community, including perhaps somebody you've had on your show, who think that it is possible. You can just keep extending life, and that'll buy you enough time to do more research, and you'll extend more life.
And there's a generation that would reach the escape velocity.
Exactly.
Where the prolonging of your life is 1 year per year, and then you live forever. Yeah.
Now, I'm highly skeptical, as are most scientists in this field, because aging is a multifactorial process, and to be able to do this in a way that's safe, that's efficacious, that actually works, I think it's going to be very, very hard.
Yeah,
certainly
but
not impossible.
The Google software that uses AI for folding proteins, which won a Nobel Prize, if memory serves, won't that solve all your protein folding problems?
No, this is different from... I think AI will have a big influence on biology, and maybe one day it will help with things like aging. I'd say there's also no physical or chemical law that says you can't colonize other galaxies or even Mars. And so,
Why would we want to?
Whatever Elon may say, it's not going to happen tomorrow.
All right, so what happens the day we achieve escape velocity? What happens to civilization?
I think before that, a number of things will happen. For example, more people may live to be 100 or well into their 90s or early 100s. That itself will cause a huge shift in society. For example, fertility rates everywhere are dropping. And so what you're going to have is a
It's
society.
an aging of the population.
Society where there's very little turnover. Same people are living longer and longer, very, very slow turnover. To me, that means a less dynamic and less vibrant society. If you look at the history of science or any fields, even literature, people have done their most creative work when they're young. And it's not just about physiological age. When you're young, you're looking at things fresh. You're not as opinionated. You're not dogmatic, and that allows you to think out of the box.
You have to convince the old people that they're less useful to society. How do you do that?
That's one of the reasons I'm retiring is because I decided 4 or 5 years ago to close down my lab. It's going to happen late this year. It's partly because I do believe that when you've had your time, you should step aside and let younger people carry on.
When Einstein was given the option to be operated on, basically on his deathbed, he said, "No, my work is done."
My work is done.
What you were talking about is inverting the population pyramid. So it goes from a small peak of aging population to a rather large one and less young people. I mean, we are basically diving down a drain here.
But what it would be? It would be more stable the whole time.
More stable.
So-
A stable thing would be good. But if the turnover is very slow and people just live for very long, I mean, as people get older, they accumulate power, they accumulate wealth, they accumulate influence. And of course, the three go together. And that then means that it's harder for younger people
to gain entrance.
To gain
Right.
entrance, to make it, and so on.
To make headway.
And that's a real problem.
Sociocultural fact.
Yes.
And that's a
And you're
that's a
so
real problem.
we're seeing that right now in a certain party in America where they're like, "Yo, everybody who is in charge is 80 years old. Get out of the way because we have a different way to do things and we want to get to it."
Interesting.
And so I think societies would be more stagnant and less dynamic and less creative. People will always throw exceptions at me. Oh, so-and-so was so brilliant late in life. But those are exceptions. That's not what you plan a society around.
Yeah.
But here's the problem. If somebody gave you a pill and said, this is going to give you 10 extra years of healthy life. Nobody wants to be sick for 10 years. 10 years of extra healthy life. Would you take it? I know I would.
Yes.
Okay? Almost all of us would. And this is the conflict between what we as individuals want and what's good for society.
Right.
And that's
Because at the end of those 10 years, if you're given the option again, you'll probably say yes again.
exactly.
Right. So that thought experiment takes the larger question down to its individual parts, and you realize people really do want to live forever.
They do well because
They do. Because this is, as you say, the only life we know. It's our existence. We fear the loss of existence. And that's the
But
problem.
there's. I mean, I'm about to get philosophical. The great thing about death is that when you look at it full on and embrace it for what it is, it allows you to wake up and treat each day as something special because you know this thing is going to be over.
Having a finite life gives you the drive, the incentive to accomplish things. Otherwise, there's always tomorrow.
There's always tomorrow.
Okay, so that is true. But at the same time, there's an old joke. Who would want to live to be 100? And the answer is always someone who's 99.
Yeah.
You may be philosophical about death in the abstract. You don't want to die next year. There's also one aspect of aging research. If you ask most of them, they'll say, except for some of these outliers, they'll say, oh, we're not about extending lifespan. We're about increasing health in your life. And the idea is that you stay healthy all your life and then suddenly, crash and die. And there's a poem called The One-Horse Open Shay.
I just learned about that poem. Okay.
The carriage was perfectly designed so that it wore out, all its parts wore out equally.
Exactly at the same time.
And one minute the farmer was riding along, the next minute he was on the ground surrounded by a bunch of debris because his whole carriage had
fell
collapsed.
apart.
Now that's what people are asking when you say we're going to compress the period of morbidity in old age and we're just going to suddenly decline and die. Nobody's shown that can actually happen. If they increase our health span, it's equally possible
I like
that
that.
they may
Health
extend.
span. Good phrase. Not lifespan, health span.
Yeah, but if they do that, if they keep us healthy in old age, it's equally possible that they extend our lives
Yeah.
too. And that eventually we still have that slow decline.
Oh, you still have
You just reach a point where now I'm 108 and it's all falling apart, but I'm not going to die tomorrow. It's still going to be a slow,
Another
arduous
5 years
death
or
5
something.
years from now.
Yeah. Of course, if we live forever, we need to find another planet because the population will continue to rise and we will outstrip the resources of Earth and possibly Mars, Venus, and any place else we search for.
That isn't quite true.
If birth rate went to 0, then it's not a problem.
Exactly.
But who
Or
wants
birth-
that?
Well, first of all, you're not going to have complete immortality. You're going to have extended lifespan. So the birth rate simply has to fall in accordance with how much you've increased your lifespan.
There you go.
And in fact, if you look at Korea, South Korea,
It's happening
or Japan,
anyway.
it's happening. People are living longer, and yet the population's going,
Going down.
So Venki, this conversation has been delightful and illuminating and enlightening. On this topic of why we die, we covered so many nuances of it. I'm left with very little to offer as a cosmic perspective. What I will say is that, speaking for myself, echoing the sentiments of others, I, at this stage in my life, value the knowledge that I will die because that gives meaning to every day that I'm alive, knowing that there's one fewer days left in my future to love, to have new ideas, to make discoveries, to embrace all that it is to be alive in this world. If you look at it mathematically, if the knowledge of death is what brings meaning to being alive, then to live forever is to live a life with no meaning at all. If you can just put off to tomorrow what you could have done today. Will I think this on my deathbed? If I'm offered a pill that can make me live another 10 years, when I'm on my deathbed, would I take that pill? I don't know. It's kind of easy to talk about death when I'm pretty sure I'm not near it in this moment. But I will say, I reserve the right to revisit the option of living a little longer when I'm on my deathbed. But for now, knowing I'm going to die is what's keeping me going. And that is a cosmic perspective.